What if the problems that take today's fastest computers centuries to crack could be solved in seconds? This isn't some distant fantasy, it's the reality that quantum physics is bringing closer than ever. As researchers push the limits of quantum computing, classical machines face a challenge they may never overcome. In this documentary, we'll explore the new breakthroughs that could change everything we know about ourselves and the universe. Quantum supremacy is a term used to describe a point in time when a quantum computer can perform a specific task faster than any classical computer. To understand this better, think of classical computers as extremely fast and clever calculators, handling tasks by processing bits of information as either 1 or 0. In contrast, quantum computers operate using quantum bits or qubits, which can exist in multiple states at once. This peculiar ability allows them to solve complex problems that would take ordinary computers years to tackle. Imagine trying to find your way through a maze. A classical computer might test every path one after the other, taking a considerable amount of time to reach the exit. Meanwhile, a quantum computer can explore many paths at the same time. This parallelism gives quantum computers a significant advantage in specific calculations, especially in fields like cryptography, material science, and complex system modeling. The importance of quantum supremacy lies in its potential to revolutionize technology and science. Once established, it opens new doors for solving previously intractable problems and enhances our understanding of the universe. It could lead to breakthroughs in drug discovery, climate modeling, and even artificial intelligence. However, reaching this milestone represents just the beginning of what quantum computing can achieve. The real challenge is developing reliable quantum computers that can consistently outperform their classical counterparts in practical applications. Thus, quantum supremacy is not only a scientific achievement, but also a stepping stone toward a new era of computational power and innovation. Quantum computing represents a revolutionary leap from classical computing, which has been the foundation of our digital world for decades. While conventional computers process information in a binary form, using bits that can either be 0 or 1, quantum computers utilize quantum bits, or qubits. These qubits can exist in multiple states at once thanks to a principle called superposition. Imagine spinning a coin in the air. While it's spinning, it's not just heads or tails, it embodies both possibilities at the same time. This ability allows quantum computers to handle vast amounts of information simultaneously, making them incredibly powerful for certain complex tasks. Another key difference is entanglement. When two qubits become entangled, the state of one qubit instantly influences the state of another, no matter how far they are apart. This connectedness allows quantum computers to perform coordinated calculations in ways that classical computers cannot. Think of it as a team of dancers perfectly in sync, effortlessly moving together, regardless of the distance between them. Because of these unique properties, quantum computing holds great promise for solving specific problems much faster than classical computers can. It could unlock advancements in areas like cryptography, optimization, and simulation of quantum systems. However, building practical quantum computers remains a significant challenge due to their sensitivity to environmental factors and the complex nature of quantum states. As we uncover more about quantum mechanics, the potential of quantum computing continues to inspire and intrigue scientists and technologists alike. Achieving practical quantum supremacy brings several significant challenges that scientists and engineers are actively working to overcome. At its core, quantum supremacy refers to the point where a quantum computer can perform computations that are infeasible for even the most powerful classical computers. One major challenge is maintaining qubit stability. Qubits, which are the building blocks of quantum computing, are delicate and easily disturbed by their environment. This sensitivity leads to errors in calculations. To combat this, researchers must develop effective error correction methods, which can be complicated and resource-intensive. These methods are necessary to ensure that the computations achieve accurate results, despite the inherent instability of qubits. Another challenge is scaling up the number of qubits effectively. While some experiments have successfully demonstrated quantum operations with a small number of qubits, increasing this number while maintaining coherence and error correction becomes much more complex. This scaling needs new materials and innovative engineering techniques to build larger quantum systems that can operate efficiently. Additionally, there is the challenge of developing algorithms that can take full advantage of quantum computing's unique capabilities. Many existing algorithms are designed for classical computers and may not translate effectively to quantum systems. Researchers must discover new algorithms that can exploit quantum entanglement and superposition, which are essential features of quantum mechanics. Finally, a pragmatic, real-world application of quantum supremacy is crucial. Achieving theoretical breakthroughs in a lab is one thing, but demonstrating practical benefits for industries such as finance, drug discovery, or materials science is another. This requires collaboration between scientists, industry partners, and policymakers to define problems that quantum computers can solve more effectively than classical counterparts. Overcoming these challenges will not only demonstrate the power of quantum computing, but also pave the way for its integration into everyday technology. Quantum computing is an exciting frontier, attracting significant interest and investment from both private companies and research institutions around the globe. Among the leaders in this field, certain companies have emerged as key players. First, there is IBM, a pioneer in computing technologies. Their approach to quantum computing includes offering cloud access to their quantum systems. Researchers and developers can experiment with quantum algorithms using real quantum computers. Additionally, they have established a framework for building quantum applications, known as Qiskit. Next up is Google, known for its ambitious quests in computing. Their breakthrough came with the announcement of quantum supremacy, which meant they performed a calculation that would take classical computers thousands of years to achieve. Google continues to innovate and push the boundaries of what quantum systems can do. Microsoft is also making significant strides, particularly with their Azure quantum platform. They focus on creating software and tools for quantum development and are investing in hybrid computing efforts that combine traditional and quantum methods. Another notable player is Rigetti Computing, a startup focused on quantum hardware and software integration. They have developed their own quantum chips and offer cloud-based quantum computing services as well. Moving to academia, institutions like the Massachusetts Institute of Technology stand out for their research contributions and collaborations with industry. MIT's research spans various aspects of quantum technologies, exploring the theoretical and practical implications of quantum mechanics. The University of California, Berkeley, and Stanford University also have dedicated research labs specially aimed at advancing quantum computing. Their teams work on quantum algorithms, error correction, and foundational theories, often collaborating with tech companies to bridge the gap between research and real-world applications. In Europe, the European Organization for Nuclear Research, commonly known as CERN, is also exploring the potential of quantum computing, particularly for applications in particle physics and data analysis. Together, these companies and institutions are driving the development of quantum computing, each making unique contributions that could shape the future of technology. Their collective aim is to unlock the potential that this form of computing promises, which could revolutionize areas such as cryptography, material science, and complex system simulations. Quantum advantage and quantum supremacy are two important concepts in the realm of quantum computing, and while they may sound similar, they address different aspects of what quantum computers can achieve. Quantum supremacy refers to the point at which a quantum computer performs a calculation that is impossible or would take an impractically long time for the most advanced classical computers to complete. It's like a significant milestone, showing that quantum computers can solve certain problems faster than classical computers ever could, regardless of practical usefulness. This was famously demonstrated when a specific quantum task, difficult for traditional systems, was completed rapidly by a quantum computer. On the other hand, quantum advantage is a broader and more practical concept. It describes the situation where a quantum computer performs a task more efficiently than a classical computer, but this task is relevant in real-world applications. Essentially, while supremacy is about proving potential, advantage is focused on effectiveness in solving problems that matter, such as optimization challenges or complex simulations that could lead to breakthroughs in various fields. To summarize, while quantum supremacy marks a triumph in computational capability, Quantum advantage emphasizes the practical benefits and efficiencies that quantum technology can bring, demonstrating its usefulness in everyday applications. Each concept highlights the evolving power of quantum computing as it continues to develop and redefine the boundaries of technology. Quantum computing has the potential to revolutionize several industries, including finance, cybersecurity, and artificial intelligence. In finance, this technology can analyze vast amounts of data at incredible speeds. Imagine being able to assess thousands of investment strategies or market scenarios simultaneously. This rapid calculation could lead to more informed decision-making, resulting in much faster responses to market changes and potentially increased profits. When it comes to cybersecurity, quantum computing presents both challenges and opportunities. On one hand, its computational power could break traditional encryption methods, making current security systems vulnerable. This raises concerns about data protection and online safety. On the other hand, quantum mechanics can also lead to the creation of new, more secure encryption methods. These methods harness the unpredictable nature of quantum particles, creating security systems that are almost impossible to breach, bolstering the safety of sensitive information. In the realm of artificial intelligence, quantum computing offers the ability to enhance machine learning algorithms. Traditional computers process information using a binary system, which can limit their ability to handle complex problems efficiently. Quantum computers, however, can operate using qubits that exist in multiple states at once. This capability means they can explore numerous solutions simultaneously. As a result, AI systems could become better at recognizing patterns, making predictions, and improving their own algorithms by learning from data much faster than before. Overall, while quantum computing holds incredible promise, it also brings challenges that industries will need to navigate to fully harness its benefits. The future may see a transformation in how industries like finance, cybersecurity, and AI operate, leading to innovations that could reshape the way we live and work. Quantum computers and classical supercomputers serve different purposes, and it's crucial to understand their unique strengths. At their core, quantum computers manipulate information using the principles of quantum mechanics. They use bits that can exist in multiple states at once, thanks to a property called superposition. This allows them to process vast amounts of data simultaneously, making them potentially faster for specific tasks like factoring large numbers or simulating complex quantum systems. On the other hand, classical supercomputers are built on traditional bits, which can be either in an off or on state. They excel at a wide range of computations, from weather forecasting to scientific simulations. These machines can handle massive datasets and perform calculations in a reliable manner. While quantum computers show great promise, especially in fields like cryptography, material science, and optimization problems, they are not universally better than supercomputers. Many tasks, especially those involving straightforward calculations or processes that do not leverage quantum properties, are still best suited for classical systems. Moreover, quantum technology is still in its infancy, facing challenges such as error rates and the need for extremely low temperatures to function effectively. As research progresses, it will likely lead to a hybrid approach where both quantum and classical systems complement each other, utilizing their individual strengths for various applications. This collaboration could elevate our overall computational capabilities rather than pursuing a complete replacement of one by the other. Quantum algorithms open up exciting possibilities for solving problems that are currently very challenging for traditional computers. One of the most promising quantum algorithms is known as Shor's algorithm. This algorithm has the potential to break widely used encryption methods by factoring large numbers much more efficiently than traditional methods. Imagine trying to find two smaller numbers that, when multiplied together, equal a very large number. While a classical computer would take an enormous amount of time, a quantum computer could do this in a fraction of that time, thanks to its unique way of processing information. Another significant quantum algorithm is called Grover's algorithm. This algorithm searches through unsorted data much faster than classical algorithms could. Instead of examining each item one by one, which can take a long time, Grover's approach uses the principles of quantum superposition to explore many possibilities at once. It's like having a superpower that allows you to peek at numerous items in a treasure chest simultaneously, significantly speeding up the search process. Then there's the Quantum Approximate Optimization Algorithm, or QOA. This algorithm is designed for solving optimization problems, where you want to find the best solution out of many options. It leverages the concepts of quantum entanglement to explore various combinations and determine the most effective outcome more efficiently than classical optimization methods. Lastly, we should mention the quantum simulation algorithms. These allow scientists to simulate quantum systems, which is extremely hard for traditional computers. Since nature itself operates on quantum principles, simulating these systems can provide insights into complex materials, reactions in chemistry, or phenomena in physics that remain mysterious. Quantum algorithms utilize the unique properties of quantum mechanics, including superposition and entanglement. This harnesses the vast potential of quantum states to perform calculations and searches in ways that were once thought impossible. As research continues, these algorithms might reshape computing and open new avenues in various fields, from cryptography to materials science. Quantum computing introduces fascinating concepts that resonate with the idea of parallel universes. At its core, quantum computing harnesses the principles of quantum mechanics, which govern how tiny particles behave. Unlike classical computers, which handle bits as either zeros or ones, quantum computers utilize quantum bits, known as qubits. These qubits can exist in multiple states simultaneously, much like a spinning coin. Now, relating this to parallel universes, we find a captivating theory known as the many worlds interpretation of quantum mechanics. According to this interpretation, every time a quantum event occurs with different possible outcomes, like the flip of our coin, each outcome leads to the creation of distinct branches in the spectrum of reality. Imagine each possible result forming a new universe where that specific outcome took place. In a way, a quantum computer can explore multiple possibilities at once, much as if it were navigating through a web of these parallel universes. When it performs calculations, it examines many potential paths simultaneously instead of following just a single route, allowing it to solve complex problems far more quickly than traditional methods. This extraordinary capability highlights how the behaviors of quantum particles mirror the idea of multiple realities coexisting alongside one another. As quantum computers process information, it's as if they are tapping into a realm of endless possibilities, reflecting the fascinating concept that every choice branches out into its own universe. This connection between quantum computing and parallel worlds paints a vivid picture of how cutting-edge technology might be intertwined with the deepest mysteries of reality itself. The ultimate real-world application of a fully functional quantum computer lies in its ability to tackle problems that are currently insurmountable for traditional computers. Imagine a powerful machine that can analyze vast amounts of data and perform complex calculations at extraordinary speeds. This technology opens possibilities across multiple fields. In medicine, quantum computers could revolutionize drug discovery by rapidly simulating the interactions of molecules. Current methods can take years to predict how a new drug will interact with the body or its target disease. With quantum capabilities, researchers could explore countless combinations of molecules almost instantaneously, accelerating the development of effective treatments. Additionally, in the realm of cryptography, quantum computers hold the potential to break encryption methods that protect sensitive data today. Conversely, they could also create new, unbreakable encryption techniques, thereby enhancing cybersecurity for everything from personal communications to national security. Quantum computing could also have profound implications for materials science. By simulating how different materials behave at the quantum level, scientists could design new materials with specific properties. Think lighter, stronger composites for use in everything from aerospace to electronics. Astrophysics stands to benefit too. The complexities of simulating cosmic phenomena, like black holes or the early universe, would become manageable with quantum computing. Understanding these mysteries could reshape our understanding of the universe itself. In finance, managing and analyzing complex risk portfolios could also be transformed. Quantum computers could optimize investment strategies and detect fraudulent activities in real time, leading to more stable and secure markets. These examples merely scratch the surface. As quantum technology matures, its influence could span every sector, ushering in a new era of innovation and discovery that reshapes our world. The implications of harnessing this power are not just theoretical. They carry the potential to transform our everyday lives. Error correction is one of the most significant challenges in quantum computing due to the delicate nature of quantum states. In the world of quantum mechanics, particles can exist in multiple states at once, a property known as superposition. This is in stark contrast to classical bits in traditional computers, which are either a 1 or a 0. While superposition allows quantum computers to process vast amounts of information simultaneously, it also makes them susceptible to errors from even the smallest environmental disturbances, such as temperature changes or stray electromagnetic fields. Additionally, quantum bits or qubits can experience a phenomenon called decoherence. This is when the quantum system loses its unique quantum properties and behaves more like classical bits due to interactions with the surrounding environment. When decoherence occurs, the information stored in the qubits can be disrupted or lost. Consequently, the fragile nature of quantum states means that when performing computations, the accumulated errors can quickly undermine the results. To tackle this issue, quantum error correction codes are designed to identify and fix errors without directly measuring the qubits, which would collapse their quantum state. This process involves encoding the information across multiple qubits, creating redundancy so that even if some aspects fail, the original information remains intact. However, this requires an immense number of physical qubits to accurately maintain and recover the information, far more than needed in traditional computing. The complexity of building reliable quantum error correction systems means researchers are continually innovating and experimenting with new approaches. Even though great strides have been made, error correction remains a significant barrier to scaling up quantum computers to practical levels, as achieving a fault-tolerant quantum processor capable of completing complex computations is crucial for realizing their full potential. Addressing this hurdle is a step toward harnessing the extraordinary power of quantum computing in solving problems far beyond the capabilities of today's classical systems. In quantum systems, errors happen because particles like electrons or photons behave in ways that are fundamentally different from what we see in our everyday lives. Instead of being like tiny balls that can be easily tracked, these particles can exist in multiple states at once. This is called superposition. When we try to measure or observe these particles, they suddenly choose a state, affecting the outcome in ways that are often unpredictable. This inherently uncertain nature is compounded by another phenomenon known as entanglement, where particles become linked to one another in such a way that the state of one can instantly influence the state of another, no matter how far apart they are. If one particle experiences an error, it can cause a chain reaction that influences its entangled partners, complicating the entire system. Fixing these errors is challenging for several reasons. First, the act of measuring a quantum state can inadvertently change it, leading to more issues. Second, quantum systems are extremely sensitive to their environments. Even tiny disturbances from surrounding electromagnetic fields or temperature changes can introduce errors. This means that keeping the system isolated and stable is a constant battle. Moreover, traditional error correction methods used in classical computing do not translate easily to the quantum realm. Classical systems can duplicate and track bits of information, but in quantum systems, the information contained in a qubit, the quantum equivalent of a bit, cannot be simply copied or restored without affecting it. Instead, researchers are exploring ways to apply quantum error correction techniques that involve encoding information across multiple qubits, but these methods are complex and require significant resources. As we strive to develop practical quantum technologies, addressing these errors is crucial because even a tiny mistake in the quantum world can lead to entirely incorrect results, making reliable quantum computing and communication a profound and ongoing challenge. Quantum error correction is a fascinating area of research aimed at safeguarding the fragile information stored in quantum states. Unlike classical bits, which can be easily copied and corrected, quantum bits or qubits have unique properties that require specialized techniques to protect them against errors caused by their environment. One promising approach involves the use of what are known as stabilizer codes. This technique leverages specific patterns of qubit entanglement to detect and correct errors. Essentially, a set of qubits is used to represent a single logical qubit, distributing the information across multiple physical qubits. If an error occurs, the stabilizer measurements help identify the affected qubits, enabling a correction without directly measuring the logical qubit itself, which could cause further disruption. Another significant strategy revolves around surface codes. These codes arrange qubits on a two-dimensional grid, allowing for efficient error correction. By focusing on local interactions between qubits, surface codes offer robust fault tolerance, making them well-suited for implementation in actual quantum computing systems. They can protect against qubit errors and also handle errors that might arise due to the challenging nature of quantum hardware over time. Additionally, topological codes are gaining traction in the field. They rely on the principles of topology, which is the study of shapes and spaces, to provide protection against local disturbances. By encoding information in such a way that it's spread across a network of entangled qubits, topological codes can maintain the integrity of quantum information even when individual qubits experience errors. Lastly, although still largely experimental, CAT codes represent an exciting frontier in quantum error correction. These codes take advantage of superposition, where two states can coexist, to create a robust form of error correction. By encoding logical qubits in a superposition of states, they allow for potential resilience against certain types of noise. As researchers continue to explore these various approaches, the goal remains to create a stable and reliable quantum computer capable of performing complex calculations without losing valuable data to errors. The understanding and implementation of these error correction methods will be paramount in advancing the field of quantum computing. In the world of quantum computing, qubits are the fundamental building blocks, much like bits in a classical computer. However, qubits behave quite differently and are uniquely sensitive to their environment, leading to errors in calculations. When more qubits are added to a quantum system, the way they interact can help manage these errors more effectively. Imagine you're trying to send a message, but there's a lot of noise in the environment that can alter the words. If you send one message, it might get distorted and become unreadable. However, if you send multiple copies of that message, each modified in a specific way, you increase your chances of ensuring that at least one copy arrives clearly. This concept is similar in quantum computing, where adding more qubits allows for the use of special techniques known as quantum error correction. Quantum error correction involves creating entangled states where the information is spread out over multiple qubits. This way, if one qubit experiences an error due to environmental interference, like being altered by stray electromagnetic fields, other qubits can help identify and correct that error without losing the overall quantum state. This ensures that the calculation remains valid. Moreover, as the number of qubits grows, so does the potential complexity of the computations they can perform. This expanded capacity means that algorithms specifically designed to work with multiple qubits can harness quantum parallelism, effectively finding solutions faster while managing errors more efficiently. Thus, increasing the number of qubits isn't just about conducting more calculations, it's about enhancing the reliability of those calculations, allowing quantum computers to function more accurately in the face of the inevitable challenges posed by their delicate nature. The journey toward a completely error-free quantum computer is both fascinating and complex. At the heart of quantum computing lies the behavior of tiny particles like atoms and photons, which possess unique qualities such as being in multiple states at once, or superposition. However, these particles are also highly sensitive to their surroundings. This sensitivity can lead to errors during calculations, as even the slightest disturbance might change their state, much like how a gentle breeze can cause ripples on a calm lake. Scientists are currently developing methods to reduce these errors, such as error correction techniques tailored for quantum systems. Imagine needing a backup plan every time you play your favorite game. This is similar to what researchers must do with quantum information. They have to create logical qubits that can detect and correct mistakes in quantum data, striving to maintain accuracy despite disturbances. While progress is substantial, achieving a completely error-free quantum computer is a formidable challenge. This is not merely about fixing today's problems, it involves fundamental changes in how we understand and manipulate quantum states. Researchers are exploring advanced materials and error-tolerant algorithms, which may enhance stabilization, but a total elimination of errors remains a difficult goal. In the future, It's plausible that we could make significant strides toward reducing quantum errors to a point where they are negligible for most practical purposes. Such a breakthrough would allow quantum computers to tackle problems considered impossible for classical systems today, transforming fields like cryptography, medicine, and artificial intelligence. However, for now, the quest for perfection continues, balancing optimism with realism as scientists unravel the mysteries of the quantum realm. Error correction plays a vital role in the development of a quantum internet. Error correction plays a vital role in the development of a quantum internet. To understand this, let's consider how a traditional internet transmits information. It sends data in the form of bits, either a 0 or a 1, and uses error correction techniques to ensure that even if parts of the data are lost or corrupted during transmission, the original message can still be reconstructed. Now, in the realm of quantum mechanics, things get more complex due to the nature of quantum bits, or qubits. Unlike regular bits, which are always either 0 or 1, qubits can be both at the same time thanks to a property known as superposition. This gives quantum computing its incredible power, but also introduces greater susceptibility to errors caused by the environment, like noise or interference. Due to these fragile states, a qubit can easily lose its information through a phenomenon called decoherence. This is where error correction becomes essential. Quantum error correction involves creating redundant systems where the information is encoded in such a way that it can withstand errors without losing the overall message. Instead of simply duplicating the data, which wouldn't work in the quantum world due to the rules of superposition, scientists create entangled states where multiple qubits work together. By doing this, they can detect and correct errors without measuring the qubits directly, which would disrupt them. Imagine trying to listen to a musician performing in a crowded room. If some notes are obscured by noise, having several musicians play the same piece allows the listener to piece together the correct melody. In a similar way, quantum error correction allows a quantum internet to maintain coherent communication across vast distances, even if some qubits encounter disturbances. As researchers continue to refine these techniques, the potential for a quantum internet becomes more tangible. This network promises to enable ultra-secure communication and the distribution of quantum information in ways that the classical internet cannot match. However, achieving reliable error correction is one of the major challenges. With robust systems in place, the dream of a functional quantum internet may soon transition from theoretical exploration to a groundbreaking reality. Redundancy in quantum circuits is crucial for enhancing their stability and overall performance. To understand this, imagine a group of people working on a project. If one person makes an error, others can pick up the slack and continue towards completion. Similarly, in quantum circuits, redundancy means having multiple qubits perform the same task or represent the same information. This approach acts as a safety net. Quantum bits or qubits are particularly vulnerable to disturbances from their environment, which can lead to errors in calculations. By duplicating information across several qubits, the system can identify and correct mistakes that arise due to noise or interference. This is akin to having backup systems in place in any complex machinery. If one component fails, another can take over without losing progress. On a technical level, redundancy allows for greater error correction capabilities. When the quantum state is encoded in multiple qubits, the circuit can employ various techniques to determine what the true state should be. Even if some qubits fluctuate or behave unexpectedly, the information can still be preserved and utilized correctly. This resilience is vital for practical quantum computing, where accurate and reliable results are necessary for tasks ranging from complex simulations to secure communications. Redundancy in quantum circuits promotes stability by providing multiple pathways for information. It ensures that even in the face of errors, the system can recover, thereby moving us closer to realizing the full potential of quantum technology. Quantum error-correcting codes are essential tools in the field of quantum computing, designed to protect qubits, the basic units of quantum information, from errors that may arise during computations. Just like in classical computing, where errors can occur due to noise or interference, quantum systems are particularly susceptible to decay and disturbances from their environment. One of the primary types of quantum error-correcting codes is the Shor code. This code cleverly combines classical error correction techniques with quantum mechanics. It encodes a single qubit of information into a larger set of qubits, specifically using 9 qubits to represent 1. This redundancy helps identify and correct errors without measuring the actual qubit directly, preserving the quantum state. Another important code is the 5-qubit code, which is known for its efficiency in protecting against specific types of errors, primarily bit flip errors and phase flip errors. This method takes advantage of the structure of quantum states, encoding information so that it can tolerate and correct multiple types of disruptions. Then there's the surface code, which uses a 2-dimensional grid layout of qubits. Its design allows for efficient error correction by localizing corrections to nearby qubits. This arrangement makes it particularly attractive for large-scale quantum computing, as it simplifies the physical design of quantum processors. Lastly, there are concatenated codes, which build on existing codes by nesting them within each other. This multi-layered approach can significantly enhance error correction capabilities and make it resilient against various types of noise over long periods. Each of these codes plays a crucial role in advancing quantum technology, ensuring that quantum systems can perform complex computations while being shielded from potential errors that could undermine their performance. By constantly improving and developing quantum error-correcting techniques, researchers are paving the way for more reliable and powerful quantum computers in the future. Quantum computers hold immense potential for solving complex problems, but they face a significant challenge known as quantum errors. These errors arise due to various factors, such as environmental interference or imperfect operations. To maintain the delicate quantum states necessary for computation, effective error correction methods are crucial. Artificial intelligence can play a transformative role in enhancing quantum error correction techniques. Imagine a scenario where AI acts like a skilled navigator, identifying and addressing the different types of errors that may occur within a quantum system. Using vast amounts of data, AI can learn patterns in how errors manifest and develop strategies to mitigate them. One way AI can assist is through optimization. It can help design better error-correcting codes that can efficiently detect and fix errors without disrupting the quantum information. This process involves figuring out the most effective ways to protect qubits, which are the building blocks of quantum computers. Additionally, AI can simulate quantum systems under various conditions to predict where errors are likely to happen. By running these simulations, researchers can get insights that lead to improvements in real quantum circuits. Furthermore, as quantum technology continues to evolve, AI can adapt and optimize error correction methods in real time, ensuring they remain effective in dynamic environments. Combining the analytical power of AI with quantum physics has the potential to revolutionize quantum error correction, making quantum computers more robust and reliable for future advancements. With improved methods, we could see significant strides in harnessing the full power of quantum computing, possibly solving problems far beyond the reach of classical computers. Quantum computing holds the promise of transforming how we process information by harnessing the strange properties of quantum physics. However, realizing scalable and fault-tolerant quantum computers remains a significant challenge. Currently, researchers have made strides in creating small quantum systems that can perform basic computations. These systems utilize tiny particles like atoms or photons to represent information in a way that traditional computers can't. But as we try to scale these systems up to handle more complex tasks, we face issues like noise, unwanted disturbances that can cause errors in calculations. Fault tolerance is crucial for practical quantum computing. This means that a quantum computer must be able to correct errors without interrupting its calculations. Just like how error-correcting codes allow our classical computers to handle problems without crashing, quantum systems also need similar methods, but the mechanics of doing this are far more complicated due to the nature of quantum bits, or qubits. Currently, researchers are exploring various approaches to stabilize and scale these systems, like using specific arrangements of qubits that exploit their interactions to maintain coherence or alignment of their states. Progress continues to unfold, but achieving full scalability where quantum computers can perform practical, reliable tasks is still a few years away. As technology advances, the hope is to gradually unlock the power of quantum computing, which could revolutionize fields like cryptography, materials science, and complex problem solving. leading us closer to creating powerful, fault-tolerant quantum computers. Quantum entanglement is a fascinating phenomenon in the realm of quantum physics, where two particles become interconnected in such a way that the state of one instantly influences the state of the other, regardless of the distance separating them. Imagine two dancers who, no matter how far apart they are, can mirror each other's movements perfectly. When one spins, the other spins instantly, as if they share a secret connection that transcends space. This strange behavior challenges our common understanding of the universe. In our everyday experiences, when something is far away, it typically does not influence us right away. However, in the world of quantum mechanics, if these entangled particles are separated by vast distances, a change to one particle appears to be felt by the other immediately, as if they are communicating faster than light. This peculiar interaction raises questions about the nature of reality itself, suggesting that there may be a deeper connection operating beneath what we can see and measure. These connections become even more perplexing with the idea that entangled particles exist in a state of uncertainty until they are observed. Only upon measurement does one particle's state become definite, leading to a corresponding definite state in the other particle. This concept disrupts the classical view of separate, independent objects and instead suggests a mysterious intertwining of their fates. Scientists and researchers continue to explore quantum entanglement as it holds promise for advancements in technology, including quantum computing and secure communication. The strangeness lies not simply in the mechanics of entanglement, but in how it challenges our fundamental perceptions of distance, causality, and the nature of reality itself. Entanglement presents a fascinating challenge to Einstein's theory of relativity by introducing a phenomenon that seems to defy the limitations of distance and communication. In simple terms, entanglement occurs when two particles become linked in such a way that the state of one particle instantaneously affects the state of the other, no matter how far apart they are. This connection behaves like an invisible thread, carrying information between them, even if they are separated by vast distances. Einstein famously referred to this strange behavior as spooky action at a distance. His theory of relativity is based on the idea that no information or influence can travel faster than the speed of light. But entangled particles appear to violate this principle. When a measurement is made on one particle, its entangled partner instantly changes its state, regardless of the space between them. This suggests that some form of information exchange is happening beyond the traditional limits set by relativity. The implications of entanglement are profound. They force scientists to reconsider concepts of locality and causality, ideas foundational to our understanding of the universe. While relativity describes how objects and signals behave in space-time, entanglement challenges the notion that these behaviors can always be explained through local interactions. Researchers are still unraveling the mysteries of quantum mechanics, and understanding these connections could reshape our grasp of how the universe operates at its core. In this way, entanglement serves as a bridge between the strange world of quantum physics and our classical understanding of the laws of nature, prompting deeper investigations into the fabric of reality. Entanglement is a fascinating phenomenon that occurs when two particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. It's as if they share a secret connection across great distances. However, while this might sound like a possibility for faster-than-light communication, it doesn't work that way in practice. When you change the state of one particle in an entangled pair, the other particle will react immediately. But here's the catch. You cannot control what state you set on the first particle. This means that if you were trying to send a message using entangled particles, you would not be able to decide what the message is. The changes on one end occur unpredictably, so an outside observer cannot extract meaningful information from this instant connection. Additionally, no information travels between the particles in a way that can be utilized for communication. Even though the effect is immediate, the only way to verify what has happened involves a separate traditional communication method, which still travels at the speed of light. Therefore, while entanglement showcases the strange and intriguing aspects of quantum mechanics, it does not allow for faster-than-light communication as we might hope. Instead, it highlights the complexities of quantum physics and our understanding of the universe, reminding us that some connections, while instantaneous, do not defy the fundamental limits set by the laws of physics. To understand how physicists test and measure entanglement, let's start with the concept of quantum entanglement itself. Imagine two particles that are mysteriously linked. When particles are entangled, the state of one instantly affects the state of the other, regardless of the distance separating them. This strange connection is one of the central elements of quantum mechanics. In experiments, physicists often create pairs of entangled particles like photons or electrons. They use special devices called sources to generate these pairs in a way that guarantees their entangled characteristics. Once these pairs are created, researchers can send one particle to one location and the other to a different location, even far apart. To measure entanglement, scientists typically perform a series of tests known as Bell's tests. These experiments are designed to demonstrate the unique and non-intuitive nature of entangled particles. In a Bell test, physicists measure the properties of each particle, such as their polarization or spin. By analyzing the results, they look for correlations that are stronger than what is expected from classical physics, meaning these particles seem to be communicating in a way that defies normal expectations. For instance, consider measuring the polarization of each photon in a pair. If one photon is measured to be vertical, the other, when measured, will always show a corresponding polarization that reveals a deep connection, even if the photons are far apart. This pattern of results indicates that something is happening at a level that ordinary objects simply do not experience. The results of these experiments, when compared to classical theories, show remarkable agreements with quantum predictions. By continually refining their techniques, like using more sophisticated detectors to reduce noise and improve accuracy, physicists can strengthen their understanding of entanglement. They also use increasingly complex setups to explore different aspects and behaviors of entangled particles, pushing the boundaries of our current understanding of the quantum world. Ultimately, through these rigorous tests, physicists not only confirm that entanglement exists, but also explore its implications, potentially leading to advances in quantum computing, cryptography, and our fundamental understanding of reality itself. Entanglement is a fascinating aspect of quantum physics that plays a crucial role in the field of quantum cryptography. To understand this, imagine two particles that have become entangled. This means that their properties are linked in such a way that the state of one particle directly influences the state of the other, no matter how far apart they are. It's as if they share an invisible connection, communicating almost instantaneously. In quantum cryptography, entanglement ensures that any attempts to eavesdrop on the communication can be easily detected. When two parties want to securely share information, they can create a pair of entangled particles, distributing one of each pair to themselves. If anyone tries to intercept the particles or measure them, the act of doing so disturbs the entanglement. This disturbance alters the particles in a noticeable way, which alerts the communicating parties that their signal has been compromised. This method provides a robust security measure, as it fundamentally relies on the principles of quantum mechanics rather than complicated algorithms. Instead of relying on mathematical complexity, quantum cryptography's power comes from the very nature of quantum entanglement. This ensures that any unauthorized observer cannot gain information without being detected, thus allowing secure transmission of data. The use of entanglement in quantum cryptography not only safeguards communication, but also opens the door for future advancements in secure information exchange. It showcases the unique properties of the quantum world and our growing ability to harness them for practical applications. Quantum entanglement, a remarkable phenomenon where two particles become linked, does indeed raise fascinating possibilities for the transmission of information. When particles are entangled, the state of one particle instantly influences the state of another, no matter the distance separating them. It's as if they are communicating with each other faster than the speed of light. However, using this entanglement for teleporting data is a bit more complicated. Picture two friends who share secret messages. Even if they are on opposite ends of a long path, when one friend sends a message, the other can immediately read it because they share a unique connection. But here's the twist. Merely knowing one friend's message does not automatically reveal the content or allow for the direct transmission of that message. In quantum physics, To send information through entangled particles, you first need to perform a measurement on one of the particles, which in turn affects the other particle. This process does not instantly send information. It requires additional steps. Essentially, while one particle can show influence over its partner, you cannot transmit new information without sending additional classical messages through a more conventional means, which inherently takes time. So, while quantum entanglement can create a strong and immediate connection between particles, it cannot be harnessed to teleport data instantaneously on its own. Instead, it opens the door to future technologies that could enhance communication methods, potentially leading to very fast data transfer methods, but always within the limits of our current understanding of physics. When we talk about entangled particles, we are referring to a fascinating phenomenon where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. Imagine having two close friends who can finish each other's sentences, even if they are on opposite sides of the world. This is the essence of entanglement. Now, if one of the particles is altered, either by measuring its properties or changing its state, the other particle responds immediately, seemingly transcending the ordinary limitations of space. This instantaneous connection occurs even when the distance between the particles is vast, leading to intriguing implications for our understanding of the universe. What is remarkable is that this behavior does not involve any physical signal traveling between the particles at a speed we can measure. Instead, it hints at a deeper connection that challenges our traditional concepts of space-time. While scientists have devised many experiments to explore this phenomenon, we still grapple with the full implications of entanglement. It raises fundamental questions about the nature of reality, suggesting that the universe is interconnected in ways we are only beginning to understand. Moreover, experiments have shown that even when particles are separated by large distances, their entangled nature remains intact. This means that the moment you measure one particle and ascertain its state, you can know the state of the other particle with certainty. Such intriguing characteristics are not just academic. They have practical applications, including advancements in quantum computing and secure communication systems, harnessing the very nature of entanglement to develop technologies that could transform our world. The EPR paradox, named after the physicists Einstein, Podolsky, and Rosen, challenges our understanding of how particles interact and what that means for reality. In their famous paper, they presented a thought experiment about two particles that become linked or entangled, providing a unique insight into the nature of quantum mechanics. When these particles are entangled, the state of one immediately influences the state of the other, regardless of the distance between them. Imagine two entangled particles, where one spins in a certain way when observed. Instantly, the other particle, no matter how far away, perhaps on another side of the galaxy, will show the opposite spin if measured. This phenomenon raises profound questions about how information can travel faster than light and suggests that the universe might be interconnected in ways that defy our everyday experiences and intuitions. What the EPR paradox emphasizes is that if we are to fully understand reality, we may need to accept that the world operates on principles that challenge classical notions of separateness and locality. Instead of viewing objects as individual and independent, the paradox encourages us to consider that the universe is more like an intricate web, where each part is connected to another, challenging our assumptions about what it truly means for something to exist. This insight into entanglement pushes us to rethink not only the fundamental nature of particles, but also the very fabric of reality itself. Entanglement experiments are like glimpses into a mysterious and fascinating part of quantum mechanics, where the rules are not always what we expect from our everyday experiences. At the heart of these experiments is the idea of entanglement itself, which is a special connection between particles. When two or more particles become entangled, their states become linked, such that the condition of one particle instantly affects the other, no matter how far apart they are. Imagine a pair of twins who can sense each other's feelings, regardless of the distance between them. If one twin experiences joy, the other immediately knows about it, even if they are on opposite sides of the world. In the realm of quantum mechanics, this strange relationship suggests that information can appear to travel instantaneously, challenging the very nature of communication and separation. Entanglement experiments push boundaries by testing the principles that govern reality. For example, researchers often use photons or light particles to explore entanglement's effects. They can split a single photon into two entangled photons, sending one to a distant location while keeping the other close. By changing the state of one, scientists observe a synchronized change in the other, regardless of the distance between them. This phenomenon raises profound questions about causality and the flow of time. Moreover, entanglement has practical implications. It could lead to advancements in quantum computing and secure communication methods that harness these peculiar connections. Unlike traditional systems, which rely on classical bits of information that can be intercepted, quantum communication would require tapping into the entangled states, making eavesdropping nearly impossible. Through these experiments, scientists are not just probing the depths of quantum mechanics, they are rewriting our understanding of reality itself. Each discovery pushes the envelope, compelling us to reconsider concepts like separation, influence, and the very fabric of the universe. As we delve deeper into the quantum world, entanglement highlights the beautifully complex nature of existence, where particles communicate in ways that defy our daily perceptions, inviting us to look beyond the surface of reality. Entanglement is a fascinating phenomenon in quantum physics, where two particles become interconnected in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This deeply interconnected behavior raises intriguing questions about the nature of reality and the fundamental workings of the universe. When it comes to consciousness, scientists are still unraveling its many mysteries. Consciousness is the experience of awareness, our thoughts, feelings, and perceptions. Some researchers speculate that quantum mechanics, including entanglement, might play a role in how consciousness emerges. Imagine consciousness as a complex web of interactions, and entanglement might suggest that our thoughts and views could be more interconnected than we realize, linking us across different dimensions of understanding. While much remains unknown, exploring these connections could provide new perspectives. If entanglement influences how we experience reality, it might hint that consciousness is not just a product of our brains working individually, but rather a shared, interconnected experience among many. This idea proposes that understanding entanglement could reveal something fundamental about not only the universe, but also our collective experiences and our very nature as conscious beings. However, it is crucial to note that this inquiry is still highly theoretical. The link between quantum mechanics and consciousness has yet to be established clearly in the scientific community. As researchers delve deeper into the nature of both quantum phenomena and consciousness, they hope to uncover insights that could bridge these two vast domains. The journey to understand our own consciousness may just be a step away from grasping the intricate dance of entangled particles that govern the universe around us. A time crystal is a fascinating concept that challenges our traditional understanding of physics. Imagine a regular crystal like quartz, which is structured in a way that creates repeating patterns over space. Now think of a time crystal as having a repeating pattern, but instead of spanning across space, it spans through time. This means that the system oscillates or cycles through different states at regular intervals without using energy, and in a way that seems to defy our understanding of equilibrium. In most physical systems, achieving stability usually means reaching a point where things stop changing or moving. However, a time crystal remains in constant motion. Picture a pendulum that swings eternally without losing energy. That's somewhat analogous to how a time crystal operates. It continuously moves through its various phases, but instead of winding down, it keeps oscillating indefinitely. The concept defies typical physics because it challenges the second law of thermodynamics, which states that systems naturally evolve toward a state of equilibrium, where change and motion cease. Time crystals exist in a non-equilibrium state, where they maintain this perpetual motion in a highly stable manner. Their existence forces scientists to rethink foundational ideas about energy, time, and stability, opening new avenues for research that could influence future technologies and our understanding of time itself. Time crystals present a fascinating twist on the concept of traditional states of matter. While most familiar states, such as solids, liquids, and gases, are defined by their arrangement and movement of particles in space, time crystals introduce a revolutionary idea They possess an ordered structure in time instead. In a typical solid, particles are arranged in a fixed pattern, and this pattern remains constant unless significant energy is added. In contrast, a time crystal oscillates between different states without expending energy indefinitely. Imagine a clock that not only ticks perpetually, but does so in a way that creates a repeating cycle of motion in time rather than in space. These remarkable structures exhibit periodicity. They change their state at regular intervals, resembling a dance that continues on and on without tiring. This occurs due to the effects of quantum mechanics, where particles behave differently than we might expect in a classical world. A time crystal is a fascinating concept that challenges our traditional understanding of physics. Imagine a regular crystal like quartz, which is structured in a way that creates repeating patterns over space. Now think of a time crystal as having a repeating pattern, but instead of spanning across space, it spans through time. This means that the system oscillates or cycles through different states at regular intervals without using energy, and in a way that seems to defy our understanding of equilibrium. In most physical systems, achieving stability usually means reaching a point where things stop changing or moving. However, a time crystal remains in constant motion. Picture a pendulum that swings eternally without losing energy. That's somewhat analogous to how a time crystal operates. It continuously moves through its various phases, but instead of winding down, it keeps oscillating indefinitely. The concept defies typical physics because it challenges the second law of thermodynamics, which states that systems naturally evolve toward a state of equilibrium, where change and motion cease. Time crystals exist in a non-equilibrium state, where they maintain this perpetual motion in a highly stable manner. Their existence forces scientists to rethink foundational ideas about energy, time, and stability, opening new avenues for research that could influence future technologies and our understanding of time itself. Time crystals present a fascinating twist on the concept of traditional states of matter. While most familiar states, such as solids, liquids, and gases, are defined by their arrangement and movement of particles in space, time crystals introduce a revolutionary idea. They possess an ordered structure in time instead. In a typical solid, particles are arranged in a fixed pattern, and this pattern remains constant unless significant energy is added. In contrast, a time crystal oscillates between different states without expending energy indefinitely. Imagine a clock that not only ticks perpetually, but does so in a way that creates a repeating cycle of motion in time rather than in space. These remarkable structures exhibit periodicity. They change their state at regular intervals, resembling a dance that continues on and on without tiring. This occurs due to the effects of quantum mechanics, where particles behave differently than we might expect in a classical world. Furthermore, the creation of time crystals often requires very specific conditions, such as ultra-cold temperatures and manipulation of quantum bits. This contrasts with common states that can exist under a wide range of temperatures and pressures. The possibility of time crystals could lead to advancements in quantum computing, as their unique properties might be harnessed to create more powerful processing systems. While traditional states of matter are focused on spatial arrangements, time crystals expand our understanding by introducing a dynamic order based purely in the dimension of time, presenting an exciting frontier in physics that could reshape our grasp of the universe. Creating stable time crystals poses a significant challenge, primarily due to their unique requirement of maintaining a state of perpetual motion without energy loss. Imagine a crystal where not only the arrangement of its atoms is fixed in space, like regular crystals of salt or quartz, but its internal structure also rhythmically changes over time in a stable way. This means that, while a traditional crystal displays a stable shape, a time crystal exhibits an ongoing repeating pattern that does not settle into a single configuration. One of the major difficulties lies in achieving this state at a temperature that is low enough to reduce disturbances caused by thermal energy, which might disrupt the uniformity required for stability. If the temperature is too high, the atoms vibrate too wildly, preventing the periodic motion that characterizes a time crystal. Furthermore, this ongoing, predictable behavior must occur without any external input of energy, which is a fundamental requirement for the definition of a time crystal. Another hurdle is the need for precise control over the system. The interactions between particles must be delicately tuned to ensure they can synchronize and maintain their repeating cycle over time. This synchronization must remain intact, even as external factors attempt to disrupt it. Researchers are still exploring suitable materials and conditions that can sustain such stable configurations long enough to study and utilize them. The challenges of creating stable time crystals revolve around managing temperature, controlling atomic interactions, and ensuring the system remains free from energy dissipation while exhibiting continuous motion. As scientists work towards overcoming these obstacles, they inch closer to unlocking the potential applications of these extraordinary materials, which could revolutionize our understanding of time and energy. Time crystals represent an exciting frontier in physics, especially regarding quantum computing. To understand their potential use, let's first grasp what time crystals are. Unlike traditional crystals, which have structures repeating in space, time crystals exhibit a pattern that repeats in time. Imagine a pendulum swinging back and forth at fixed intervals indefinitely, showing motion without energy loss. This behavior suggests that the system can stabilize itself in a constantly oscillating state. In the context of quantum computing, time crystals could enhance the performance of quantum bits or qubits. Traditional qubits struggle with errors because they easily lose their quantum state due to environmental interference, a problem known as decoherence. The unique properties of time crystals may help in stabilizing these qubits over longer periods. Their ability to maintain coherence allows qubits to remain in their operational states more reliably, leading to more efficient computations. Furthermore, because time crystals can create periodicity in their state changes, they offer a new approach to manipulating qubits. This ongoing oscillation could potentially allow for a uniform and stable way to perform operations on qubits, making quantum operations more robust. Imagine a quantum computer powered by time crystals, executing complex calculations at speeds we have yet to achieve, thanks to reduced errors and enhanced stability. The promise of time crystals could transform not only how we build quantum computers, but also how we understand and harness the principles of quantum mechanics itself. As researchers continue to explore this fascinating area, time crystals might well pave the way for breakthroughs in quantum technology. Time crystals are a fascinating concept in physics, representing a new state of matter where the structure repeats itself not just in space, but also in time. Imagine a regular crystal, like a diamond, which has a repeating pattern in space. Now picture this same idea, but instead of living in a still arrangement, the atoms in a time crystal are constantly moving in a rhythm that repeats over time, like a pendulum swinging back and forth endlessly. While this behavior seems almost magical, creating a perpetual motion machine, something that can run indefinitely without an external energy source, is still firmly in the realm of fantasy. The laws of physics, particularly the principles of energy conservation and thermodynamics, make it clear that energy cannot be created from nothing. Even with the unique properties of time crystals, they still require energy to maintain their motion and stability. In other words, time crystals might exhibit motion that seems perpetual, but they are not a straightforward ticket to building machines that can operate without power input. There are always forces at work that will eventually lead to energy loss, whether from friction, heat, or external interactions with their environment. So while time crystals open exciting avenues for research and could revolutionize various technologies, they won't help us in achieving the dream of a perpetual motion machine. Time crystals are fascinating structures that challenge our understanding of thermodynamics and the nature of order in physical systems. At their core, these crystals exhibit a unique property. They can maintain a stable structure while exhibiting periodic changes over time without expending energy. This behavior is reminiscent of a traditional crystal, which has a repeating pattern in space. However, in the case of time crystals, that pattern repeats in time. To understand their interaction with entropy, we first need to clarify what entropy means. Entropy is a measure of disorder within a system. Generally, as time progresses, the amount of disorder in a closed system tends to increase. This is known as the second law of thermodynamics. It suggests that systems will move towards a state of greater entropy, or chaos, over time. Now, time crystals challenge this idea because they resist this usual march toward disorder. In a time crystal, even as the system undergoes changes, it manages to return to a periodic state, essentially keeping order in a way that seems contrary to the principle of increasing entropy. To picture this, imagine a pendulum that swings back and forth endlessly. Instead of becoming dampened and eventually stopping, as a typical pendulum would due to friction and other forces, a time crystal's pendulum would continue its rhythmic motion indefinitely, consistently repeating its periodic pattern. This peculiar behavior offers intriguing implications. Time crystals allow scientists to explore systems that operate out of equilibrium, where traditional thermodynamic laws may not apply in the same way. Such systems could help researchers better understand how order emerges from apparent chaos and the foundations of thermalization, which is the process by which systems reach a state of equilibrium. Time crystals do not adhere to the usual behavior dictated by entropy. They maintain a stable, ordered nature as they oscillate through different states over time. As researchers continue to investigate these extraordinary structures, they might unlock new insights about the nature of time, energy, and the fundamental rules that govern our universe. Time crystals represent an exciting frontier in the realm of physics and technology. Imagine a material that not only holds a stable state, but also exhibits a form of periodic behavior in time, akin to how traditional crystals have repeating structures in space. This unique characteristic opens up a range of potential applications that could transform various fields. One of the most promising uses of time crystals lies in the realm of computing. They could significantly enhance the efficiency and speed of quantum computers. Because time crystals maintain their state through time without dissipating energy, they could help in the development of more powerful quantum bits. This would lead to faster processing times and improved performance for handling complex calculations essential for tasks such as cryptography or artificial intelligence. In addition, time crystals may play a role in energy storage and transfer. They could help create more efficient energy systems by enabling the storage of energy in a way that minimizes waste. By utilizing their unique properties, it might be possible to develop advanced batteries or capacitors that can hold energy for longer periods without losing it. This could revolutionize everything from consumer electronics to electric vehicles. Furthermore, researchers are exploring the potential of time crystals in the field of communications. Their periodic nature might allow for more robust data transmission systems that are less prone to interference, leading to clearer signals and faster connectivity. This could greatly improve the quality of wireless communication, making it vital for applications like telecommunication networks or satellite systems. Finally, time crystals could also impact fundamental physics and our understanding of time itself. By conducting experiments with these materials, scientists can explore deeper questions about symmetry, stability, and the flow of time. This could not only expand our knowledge, but also inspire new technological innovations based on these insights. Time crystals hold the promise of revolutionizing multiple sectors through advancements in computing, energy, communication, and fundamental research, paving the way for technologies that could redefine our interactions with the physical world. Time crystals are a fascinating concept that challenge our traditional understanding of time and motion. Imagine a regular crystal, like a diamond or a piece of quartz, which has a repeating pattern in space. Now take that idea and apply it to time. That's what a time crystal represents. These unique structures display a form of motion that repeats not in space but in time, creating a state that continually cycles without the energy typically required to maintain it. This cycling behavior gives rise to intriguing connections with the idea of time loops in physics. In simple terms, a time loop is a hypothetical situation where time behaves in a circular manner. You could say it's like walking a path that eventually returns you to your starting point. In contrast, time crystals continuously cycle through their states, suggesting a kind of stability within the flow of time while still exhibiting changes. The heart of this relationship lies in the concept that both time crystals and time loops challenge the linear perception of time. In our everyday experience, time feels like a straight line, moving forward. Time crystals, however, suggest that under specific conditions, time can exhibit properties that resemble a loop or a repetition, almost as if the universe has explored its timeline to create these stable, repeating states. This interplay raises profound questions about the nature of time itself, whether it is truly linear and one-directional, or if there are ways it can curve back on itself in different forms. Ultimately, Both ideas invite scientists to explore the deeper mysteries of physics, examining how matter behaves under extreme conditions and what these behaviors reveal about the fabric of our universe. Through studying these concepts, we may uncover new insights about time's fundamental nature and the possibilities it holds for the future. Time crystals are a fascinating new phase of matter that defy our traditional understanding of time and equilibrium. Achieving their unique structures requires advanced materials and specific conditions. Currently, researchers are using a few different approaches to create time crystals, often involving highly controlled environments. One common method involves using qubits, the fundamental units of quantum computing. Specifically, superconducting materials, which allow electricity to flow without resistance at very low temperatures, are often at the heart of these experiments. These superconductors are arranged in circuits that can be manipulated to create the oscillating behaviors needed for time crystals to form. Another method utilizes ultra-cold atoms, particularly those in an ensemble where their interactions can be precisely controlled using laser light. In a recent successful experiment, researchers used a chain of atoms where the external conditions allowed them to exhibit periodic changes over time instead of reaching a stable energy state. Moreover, there are examples where certain magnetic materials have shown time crystal properties, achieved by carefully aligning spins, tiny magnetic moments, under a specific external magnetic field. This alignment enables the material to exhibit a sort of rhythmic behavior, repeating its state over time without consuming energy. In each of these cases, the essential feature of a time crystal is its ability to maintain a stable, repeating state while breaking the typical rules of thermodynamics. This blend of physics and material science continues to be a fertile area of research, hinting at exciting possibilities for future technologies in quantum computing and beyond. Time crystals are a fascinating concept that blurs the line between reality and science fiction. Imagine a crystal that not only remains stable in its structure, but also exhibits movements through time without energy input. This phenomenon arises from the unique arrangement of particles in these materials, which oscillate in a periodic fashion in their ground state. Essentially, while ordinary crystals have symmetrical structures in space, time crystals have a repeating pattern in time. This means they can change their state in a cycle, much like how swings go back and forth. Scientists have discovered time crystals in controlled laboratory settings, sparking discussions about their potential presence in the wider universe and their implications for physics. However, controlling the flow of time itself is a monumental challenge. Presently, time crystals do not allow us to speed up, slow down, or reverse time in any way we currently understand. The laws of physics, particularly as described by relativity, set firm rules about how time operates. What time crystals could do is lead to new technological advancements, such as more efficient measurements of time or breakthroughs in quantum computing. While the name time crystal suggests an ability to manipulate time, we are still far from realizing this potential. The current understanding and research are laying the groundwork for potential future applications. But as of now, we're not equipped to change the actual flow of time itself. The exploration of time crystals pushes the boundaries of our knowledge, keeping the door open for revolutionary ideas in the future. Schrödinger's cat is a thought experiment that illustrates a concept in quantum mechanics called superposition. Imagine a closed box containing a cat, a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter detects it, triggering a mechanism that releases the poison and kills the cat. If the atom does not decay, the cat remains alive. Now, in the realm of quantum mechanics, particles can be in multiple states at once until observed. This means that until someone opens the box to check, the cat is considered to be both alive and dead simultaneously. This bizarre scenario is meant to highlight the strangeness of quantum behavior and how it contrasts with our everyday experiences. The thought experiment emphasizes that, in the quantum world, reality can be uncertain and exist in multiple outcomes at the same time until a measurement is taken. When the box is opened and an observation is made, the superposition collapses into one of the two definitive states. Either the cat is alive or it is dead. Schrödinger created this illustration to criticize some interpretations of quantum mechanics. showing how peculiar and counterintuitive these ideas can be when applied to familiar situations. It encourages us to reflect on the nature of reality and observation in the quantum realm. Quantum superposition is a fascinating concept that helps us understand the behavior of particles at the smallest scales. At the heart of this idea is the notion that particles, such as electrons, can exist in multiple states at once, rather than having a single definite state. Imagine a spinning coin. While it's spinning, it is not simply heads or tails, but is in a blend of both possibilities. It is only when you catch it that it reveals either heads or tails. In the quantum world, particles can have different properties like position, energy, or spin, and they can be described as being in a superposition of those multiple possibilities simultaneously. This means that until we observe or measure the particle, it doesn't decide on one particular state. The act of measurement forces it to choose a state. This idea has real-world implications in technology and science. For example, the development of quantum computers relies heavily on superposition, as they can perform many calculations at once due to having numerous states available simultaneously. This allows them to solve complex problems much faster than traditional computers, which can only handle one state at a time. Another interesting application can be seen in quantum entanglement. This phenomenon occurs when particles become linked together, and the superposition of one can influence the state of another, no matter how far apart they are. This has led to advancements in secure communications and quantum networking. While superposition might seem strange or counterintuitive, it forms the foundation for many phenomena we observe in quantum physics, connecting the tiny world of particles to larger systems and practical applications that fundamentally shape our understanding and technology. Superposition is a key concept in quantum mechanics, where a system can exist in multiple states at once until it is measured. One of the longest durations recorded for a system being in superposition has been observed in experiments involving superconducting circuits, specifically with qubits. These qubits can maintain their superposed states for several microseconds, which might seem brief, but in the realm of quantum systems, it is significant. More remarkable are experiments with larger and more complex systems. Researchers have pushed the boundaries by achieving superposition in larger particles like molecules. For instance, in certain experiments, some larger molecules have remained in superposition for a time span that stretches into milliseconds. This is a substantial advance, as it signifies that complex entities can be manipulated in such a way that they exhibit quantum behavior over longer periods. The pursuit of maintaining superposition for even longer periods continues, as it holds great promise for advancements in quantum computing and technology. Scientists are exploring various techniques, such as isolating systems from their environment to minimize interference, which ultimately destabilizes superposition. As we learn more about these quantum properties and refine our technology, we inch closer to discovering how to sustain superposition for extended durations, a feat that could revolutionize our understanding of the quantum world and its applications. Maintaining quantum coherence is a complex challenge for scientists, largely because this delicate state is easily disrupted. To understand why, consider that quantum coherence refers to the ability of quantum particles like atoms or photons to exist in multiple states at once. This property is crucial for the development of technologies such as quantum computers, which hold the promise of solving problems much faster than traditional computers. One major obstacle is the environment where these quantum particles are located. Everything from stray magnetic fields to temperature fluctuations can introduce noise, which disrupts the delicate balance that sustains coherence. Imagine trying to hold a perfect balance on a seesaw. Even the smallest push from the outside can throw everything off kilter. Another significant challenge is scaling up systems from tiny experiments to larger, more practical applications. In small, controlled settings, scientists can sometimes manage coherence effectively. However, when attempting to apply these principles in larger arrays, such as with many qubits in a quantum computer, the chances of interference between particles increase tremendously. It's like trying to keep numerous balls in the air at once. Each additional ball adds to the complexity and the likelihood of a mishap. Furthermore, there are limitations in the materials used to create devices that harness quantum properties. Many materials have imperfections or impurities that can interact with quantum systems in unexpected ways, leading to loss of coherence. Researchers are actively looking for better materials or innovative designs to minimize these interactions and preserve quantum states for longer durations. Overall, while scientists are making progress in maintaining quantum coherence, they face ongoing challenges related to environmental interference, scaling issues, and material constraints. Addressing these problems is crucial for advancing quantum technology and unlocking its full potential. The idea of placing a living organism in quantum superposition raises fascinating questions about the intersection of biology and quantum physics. Quantum superposition refers to a state where a particle can exist in multiple states or locations at once until it is measured or observed. This phenomenon is commonly demonstrated with tiny particles like electrons or photons. Translating this concept to living organisms is far more complex. Living things are made up of countless particles, and their behavior is influenced by numerous environmental factors. As organisms become larger and more complex, they interact with their surroundings in ways that typically collapse any potential superposition into a single state. In simpler terms, living creatures are deeply embedded in their environments. They are constantly reacting to light, heat, movement, and other factors, which generally prevents them from existing in overlapping states simultaneously. However, researchers are exploring ways to investigate how quantum mechanics might play a role in biological processes. For example, some studies suggest that photosynthesis may utilize quantum effects to efficiently transfer energy. These investigations spark curiosity about whether the principles of quantum mechanics could have implications for larger systems. Nevertheless, achieving true quantum superposition in a living organism poses enormous challenges due to the delicate nature of life and the complexities of quantum states. While the notion of placing an organism in quantum superposition is scientifically intriguing, the practical realities make it seem unlikely with our current understanding. The behaviors of living systems typically resist the conditions needed for such a phenomenon, keeping the fascinating world of quantum mechanics mostly confined to the microscopic realm. When we talk about the collapse of a quantum wave function, we're diving into the strange realm of quantum mechanics. Imagine every possible outcome of a particle's behavior existing simultaneously, like a cloud of possibilities. This cloud, known as a wave function, represents all the potential states a particle could take. When a measurement occurs, like spotting the particle in a specific location, the wave function collapses. This means that the cloud of possibilities suddenly reduces to a single outcome. It's as if someone took a snapshot of the cloud at that moment, freezing it in place. The particle is no longer just a collection of probabilities. It is now in a defined state, having chosen one particular location or property. The fascinating part is that until we observe it, the particle exists in this hazy mixture. It's only when we interact with it that reality solidifies. This process challenges our everyday understanding of how things are supposed to work. The act of measurement influences what we find, raising questions about the very nature of reality. The implications are profound, suggesting that our actions as observers play a crucial role in determining what ultimately happens in the quantum world. Decoherence is a key concept that explains how quantum systems interact with their environment, leading to the transition from quantum behavior to classical behavior. To understand this, imagine a spinning coin. While it's in the air, it can be considered to exist in a state that combines both heads and tails. In the quantum world, this state is known as superposition, where particles can be in multiple states at once. However, as soon as the coin lands and we observe it, we see it either as heads or tails. This is similar to what happens in quantum systems when decoherence occurs. When a quantum system interacts with its surroundings, it becomes entangled with them. This means that the system cannot be considered in isolation anymore. Information from the quantum system is spread out into the environment, and as a result, the superposition collapses. It forces the system to take on a definite state rather than remaining in a blend of possibilities. Decoherence happens when quantum particles, like electrons or photons, come into contact with other particles, like air molecules, light, or even thermal energy. These interactions cause the delicate quantum states to lose their coherence, which is like losing the quantum magic that allows particles to behave in strange, non-classical ways. As a result, the predictable world that we experience, where things exist in one clear state, emerges. Decoherence is crucial for understanding why we don't see quantum oddities in our everyday lives. It explains the shift from quantum mechanics, where particles can explore many possibilities, to classical physics, where we can observe clear, singular outcomes. This process helps scientists navigate the complex boundaries between the quantum realm and the macroscopic world that we inhabit. Quantum superposition is a fascinating concept from quantum physics that could indeed revolutionize computing. To understand this, imagine a traditional computer as a light switch. It can be either off or on, corresponding to the binary digits known as bits, which represent data as a sequence of zeros and ones. In contrast, quantum superposition allows a quantum bit, or qubit, to exist in multiple states at the same time. Think of it like spinning a coin. While it's spinning, the coin isn't just heads or tails, it's somewhere in between, representing both possibilities. This means that a single qubit can hold more information than a regular bit. When multiple qubits are used together, they can process vast amounts of data at once. Imagine trying to find your way out of a maze. A traditional computer would explore each path one by one, while a quantum computer could explore numerous paths simultaneously due to superposition. This ability could potentially make certain calculations incredibly faster than anything possible with traditional computers. Yet, harnessing quantum superposition is not straightforward. Qubits are delicate and can easily lose their state due to outside interference, known as decoherence. Researchers are working hard to create stable environments to maintain superposition long enough to perform complex calculations. If successful, quantum computing could unlock extraordinary capabilities, such as solving problems in seconds that would take traditional computers countless years. This leap in computing power could enhance fields like cryptography, medicine, and complex system modeling, thereby transforming how we solve some of the world's most challenging problems. Superposition is a fundamental principle in quantum mechanics, where a system can exist in multiple states at once until it is measured. Testing this principle at larger scales presents significant challenges, but scientists have become quite creative. To grasp this concept, think of a classic example involving tiny particles, such as electrons, which can exist as both particle and wave. Now imagine scaling this idea up to larger objects, even those the size of small molecules. One approach involves using highly sensitive devices like interferometers. These tools can measure the interference patterns created by actions taking place within superposition, similar to how light behaves as both a wave and a particle. In one experiment, researchers have attempted to place larger systems, such as small mechanical oscillators, into a state of superposition. They achieve this by cooling these systems to near absolute zero, which minimizes any interactions with their environment. By doing so, they decrease noise and disturbances that could force the system into a single state too quickly. One of the most exciting areas of research involves using photons, or light particles. Amazing experiments have demonstrated the ability to create superposition states with complex objects made up of many atoms, showing that quantum behavior can indeed flourish on a larger scale under the right conditions. While these tests are still in the realm of advanced physics, they hint at a deeper understanding of the boundary between classical physics, the way we typically observe objects in our daily lives, and the quantum world that governs the smallest scales. Ultimately, these experiments push the limits of our understanding, exploring whether larger, more complex systems can truly embody the strange yet fascinating nature of superposition. Superposition is a fascinating concept emerging from the realm of quantum mechanics, offering profound insights into the very fabric of reality. At its essence, superposition suggests that particles such as electrons can exist in multiple states at once until they are observed or measured. Picture a coin spinning in the air. While it spins, it has the potential to be both heads and tails simultaneously. Only when it lands do we see a definite outcome. This idea challenges our everyday understanding of reality, which tends to see objects as having specific positions and states. In the quantum world, however, the act of observation plays a critical role. Before we measure or observe a particle, it exists in a blend of possibilities. This means that, on a fundamental level, reality may be more fluid and interconnected than we perceive it to be. Superposition implies that until we look, many possible outcomes coexist, intertwining like threads in a fabric. Moreover, the implications stretch beyond just particles. Superposition paves the way for revolutionary technologies such as quantum computing, where pieces of information can be processed simultaneously, vastly enhancing computational power. This notion is redefining our understanding of information, causality, and interconnectedness in the universe. Superposition reveals that what we consider to be reality might be just one thread in a tapestry of endless possibilities, continuously shaped by observation and interaction. Quantum computing poses a serious challenge to modern encryption methods by leveraging the unique principles of quantum mechanics. Traditional encryption relies on the difficulty of certain mathematical problems, like factoring large numbers or computing discrete logarithms, which take a substantial amount of time to solve using today's classical computers. A quantum computer, however, operates differently. Using the concept of superposition, a quantum bit or qubit can represent both 0 and 1 simultaneously. This ability allows quantum computers to evaluate multiple possibilities at once. Additionally, another principle known as entanglement links qubits in ways that enhance processing power significantly. One of the most concerning aspects of this new technology is a quantum algorithm called Shor's algorithm. This algorithm can factor large numbers efficiently, meaning that it could potentially break encryption that relies on the difficulty of this task. If a rogue entity wielded a sufficiently advanced quantum computer, they could decrypt communications that are currently secure, compromising sensitive data such as financial transactions, personal information, and proprietary research. Moreover, many current encryption systems could become obsolete as quantum technology progresses. As researchers explore countermeasures, the race to develop quantum-resistant encryption systems has become vital. This involves creating new methods that rely on mathematical problems that are difficult for both classical and quantum computers to solve efficiently. In sum, while quantum computing holds great promise for advancements in technology and science, it also raises critical questions about the security of the information that underpins our digital world, compelling us to rethink and improve our encryption strategies before the quantum leap becomes a reality. Shor's algorithm is a groundbreaking method developed to factor large numbers efficiently, posing significant implications for current cryptographic systems. In standard encryption methods, such as RSA, the security relies on the difficulty of breaking down a large number into its prime components. While traditional computers struggle with this task, taking an impractically long time as the numbers grow larger, Shor's algorithm changes the game. Imagine trying to crack a secret code based on a massive number that you can't easily divide. With classical algorithms, the efforts can take years or even longer. However, Shor's algorithm takes advantage of the unique properties of quantum computing, similar to having a supercharged calculator. It elegantly finds the prime factors of these large numbers by leveraging quantum bits, or qubits, which can exist in multiple states at once. The way Shor's algorithm works can be envisioned like this. First, it reduces the problem into manageable parts, using mathematical frameworks that take advantage of periodicity, a property of certain functions that repeats over time. This is analogous to finding a hidden pattern in a sea of complex data, which classical computers can't do effectively due to the sheer volume. Once the factors are identified efficiently, it essentially means that cryptographic keys, those secret numbers used to keep communications secure, can be easily retrieved by someone using this algorithm on a sufficiently powerful quantum computer. The implications of this technology are staggering because many of our most widely used security systems would no longer be safe. In short, Shor's algorithm doesn't just crack a code, it unlocks a door to vast vulnerabilities in systems we rely on for privacy and protection in our digital lives. Quantum-safe encryption methods are designed to protect information in a future where quantum computers are common. Traditional encryption relies on mathematical problems that are easy to solve in one direction, but hard to reverse. For instance, if you take two large prime numbers and multiply them together, it's simple to do. However, figuring out which two primes were multiplied to get a large number is incredibly difficult, especially as the numbers grow larger. This is the basis of many current security systems. Quantum computers have the potential to solve some of these hard problems efficiently, which means they could break traditional encryption. To counter this risk, quantum-safe encryption employs different mathematical challenges that remain difficult for both classical and quantum computers. One common approach uses lattice-based problems, which involve points in high-dimensional spaces. Imagine a multi-dimensional array with points scattered throughout. Finding the nearest point, or the smallest distance between certain arrangements in this lattice structure, is complicated, even for a powerful quantum computer. Another method is code-based encryption, which relies on error-correcting codes. Similar to how we send messages that can get corrupted during transmission. These codes can be set up in such a way that removing noise to retrieve the original message remains a tough challenge, even with advanced computing capabilities. There are also multivariate quadratic equations, in which the challenge lies in finding variables that satisfy a set of equations. This task remains exceptionally difficult, even when qubits, the basic units of quantum information, are employed to attempt a solution. By utilizing these different mathematical structures, quantum-safe encryption methods aim to ensure that our data remains secure, regardless of advances in computing technology. As we prepare for a future where quantum computing could become prevalent, these encryption methods represent a crucial step in safeguarding our digital information against potential threats. Quantum computers possess unique capabilities that make them fundamentally different from traditional computers. They operate on the principles of quantum mechanics, which allows them to process information in ways that are currently unimaginable. Essentially, while classic computers handle data as bits, which can either be 0 or 1, quantum computers use quantum bits or qubits, which can represent both 0 and 1 simultaneously. This property enables them to tackle complex problems at incredible speeds. In theory, this power could potentially allow quantum computers to break through certain types of encryption that protect government and financial systems today. Most encryption methods used currently rely on the difficulty of factoring large numbers or solving complex mathematical problems. These tasks can take traditional computers an impractically long time. However, quantum computers could utilize algorithms specifically designed for quickly solving these problems, thereby unraveling security measures that keep personal and national data secure. Despite this potential, most experts agree we are not yet at a point where quantum computers can perform such feats on a practical scale. The technology is still in its early stages and faces significant challenges, including error rates in calculations and the difficulty of maintaining qubits in stable states for meaningful computations. Additionally, organizations worldwide are actively researching new forms of encryption that would be resistant to quantum attacks. This means that while the possibility exists, it is currently more of a concern for the future rather than an imminent threat. While quantum computers have the theoretical potential to disrupt existing security systems, current technological limitations and ongoing improvements in encryption methods have created a buffer. Understanding these dynamics is crucial as we move towards a world where quantum computing becomes more pervasive. Lattice-based cryptography is a type of encryption that relies on mathematical structures called lattices. Imagine a vast three-dimensional grid where each point can represent a number. The challenge in lattice-based cryptography is to determine the shortest distance between certain points on this grid, or to find hidden patterns within it. This complexity underpins the security of lattice-based systems, making it very hard for potential attackers to break the code even with powerful computers. The importance of lattice-based cryptography lies primarily in its resistance to future threats. As technology evolves, particularly with the advancement of quantum computers, many existing encryption methods may become vulnerable. These quantum computers could perform calculations that traditional systems find extremely difficult, potentially breaking widely used encryption methods like those based on prime numbers. Lattice-based cryptography, however, is believed to be robust against such quantum attacks. It provides safety for securing sensitive data and communications in an increasingly digital world. Not only does it promise strong security, but it also holds potential for developing new types of cryptographic systems that can be used in practical applications such as secure messaging and online transactions. As the need for safety in our technology-driven society grows, lattice-based cryptography emerges as an essential tool for future-proofing our data security. The emergence of quantum computers is poised to challenge current encryption methods, which safeguard our digital communications and data. To understand the timeline for this possibility, we must consider how quantum computers operate. Unlike traditional computers, which perform calculations in a linear fashion, quantum computers leverage the principles of quantum mechanics, allowing them to analyze vast amounts of data simultaneously. Existing encryption systems, like those built on algorithms we commonly use today, largely depend on the complexity of certain mathematical problems. For example, one common form, known as public key encryption, relies on the difficulty of factoring large numbers. Classical computers struggle with this task, but quantum computers could dramatically simplify the process, making it much faster and more feasible. Predictions on when quantum computers will be powerful enough to break these encryption standards vary widely. Some experts suggest that we may see quantum computing break current encryption within the next decade, while others believe it could take several decades. A significant factor in this is the advancement of quantum technology itself, how quickly researchers can overcome existing challenges related to qubit stability and error correction. In response to this potential threat, many organizations are already exploring new encryption techniques that are designed to be secure against quantum attacks. This movement, often referred to as post-quantum cryptography, aims to create encryption methods that remain safe even in a quantum-powered future. This is an active area of research, emphasizing the need for vigilance as we navigate the evolution of technology. As we look to the future, the question is not just when quantum computers might crack existing encryption, but how quickly we can adapt our security measures. The interplay between advancements in quantum computing and the development of robust encryption will shape the security landscape for years to come. Governments around the world are actively preparing for a quantum future, recognizing the potential of quantum technology to revolutionize various fields. Imagine quantum technology as a powerful tool that can dramatically improve computing, communication, and security. To harness these benefits, many nations are investing significantly in research and development. One key area of focus is quantum computing. Traditional computers process information in bits, which can be either 0 or 1. In contrast, quantum computers operate using quantum bits or qubits, which can exist in multiple states at once. This capability allows quantum computers to tackle complex calculations much faster than classical computers. Governments are funding initiatives to build and enhance quantum computing capabilities, often partnering with universities and private companies. Another important aspect is quantum communication. This technology promises ultra-secure data transmission using the principles of quantum mechanics. For instance, quantum key distribution allows two parties to create a shared, secure encryption key using the unique characteristics of quantum particles. By investing in quantum communication infrastructure, governments aim to safeguard sensitive information from cyber threats. In addition, the development of quantum sensors is gaining traction. These sensors can detect minute changes in the environment, leading to improvements in fields such as healthcare, navigation, and environmental monitoring. Governments see the potential for enhanced capabilities in areas like precision medicine and defense, where even tiny measurements can make a significant difference. Education and workforce training are also essential components of this preparation. As the field of quantum technology requires specialized knowledge, many governments are establishing educational programs to cultivate the next generation of quantum scientists and engineers. By fostering talent in this area, they are building a strong foundation for future advancements. Moreover, international collaboration is becoming increasingly important. Countries are joining forces to share knowledge, resources, and expertise in quantum technology. This cooperation can speed up innovation and ensure that various nations can collectively address challenges related to quantum security and ethics. Governments are laying the groundwork for a quantum future by investing in research, enhancing communication security, developing new sensors, promoting education, and fostering international collaboration. These efforts signal a recognition of the profound impact quantum technology will have on society, economy, and global security in the years to come. Quantum hacking poses significant risks to several industries, primarily those that rely on data security and sensitive information. One of the most vulnerable sectors is finance. Financial institutions protect vast amounts of secure data, including customer information and transaction records. The capability of quantum computers to process information at extraordinary speeds could potentially allow hackers to break traditional encryption methods that keep this data safe. Another at-risk industry is healthcare. In this sector, patient records are often stored electronically containing personally identifiable information. If quantum hacking were to compromise this data, it could lead to breaches of privacy, identity theft, and even manipulation of medical records, all of which pose serious risks to individuals' health and privacy. Telecommunications also holds vulnerabilities. Companies that manage communications infrastructure rely on encryption to protect user data and secure connections. The emergence of quantum hacking techniques could threaten the safety of communications, making confidential conversations susceptible to interception. Government and military sectors are not exempt either. They handle sensitive national security information, and the consequences of a breach in this area could be dire. Quantum hacking abilities could expose intelligence operations or even lead to espionage, jeopardizing national security. Lastly, industries dealing with research and development, such as technology and pharmaceuticals, are at risk because they invest significant resources into innovative ideas and proprietary information. The loss of confidential research could result in immense financial losses and hinder technological advancement. As quantum technology continues to evolve, these industries will need to adapt their security measures and invest in new technologies to safeguard against potential quantum hacking threats. Quantum encryption offers a powerful approach to securing information that seems practically unbreakable under the principles of quantum mechanics. At its core, this method relies on the strange and unique behaviors of particles at the smallest scales. One key component is the use of quantum bits or qubits, which can exist in multiple states at once, unlike traditional bits that are either 0 or 1. Imagine trying to listen in on a conversation that is happening in a special room where only certain types of light can be used for communication. If someone tries to eavesdrop by measuring that light, they will disturb it. This disturbance would alert the people in the room that their conversation has been compromised. This idea is the foundation of quantum encryption, where the act of measuring the quantum state itself changes it, making it impossible for a third party to intercept the message without detection. Furthermore, quantum encryption uses a method called entanglement. When two qubits become entangled, the state of one instantly affects the state of the other, no matter how far apart they are. This phenomenon creates a level of security that is not achievable with classical encryption techniques. As long as the laws of quantum mechanics are respected, the encryption remains secure. However, while quantum encryption is incredibly secure in theory, its practical applications come with challenges. Current technology has limitations in how far these quantum signals can travel without losing integrity. Moreover, maintaining entangled states and properly implementing the technology are still areas of ongoing research. So, while quantum encryption presents a formidable shield against eavesdropping, its real-world effectiveness relies on overcoming these technological hurdles. The promise of unbreakable encryption remains alive, fueled by the ongoing advancements in our understanding of quantum physics. As we move deeper into the digital age, the need for security in our communications and transactions grows more critical. With the rise of powerful quantum computers on the horizon, we face a unique challenge. These machines could potentially crack current encryption methods, which protect sensitive information like banking details and private communications. To understand this, imagine all your important documents locked away in a safe. Right now, traditional methods of securing that safe are strong, but a quantum computer could act like a master key capable of unlocking it almost effortlessly. This raises concerns about how secure our data might be in the future. Shifting towards quantum-proof security means adopting new methods that remain secure even against the capabilities of quantum technology. This is not just about technology, it's also a global concern. Organizations, governments, and individuals need to collaborate to ensure that this transition is seamless. By investing in new protocols and systems designed to withstand quantum attacks, we prepare ourselves to protect our information in this brave new world. This shift requires not only technological advancements, but also changes in policies and an increase in public awareness. As quantum computing continues to progress, the push towards quantum-proof security must not only keep pace, but also stay ahead, ensuring that we can communicate and conduct business safely for years to come. It's an exciting yet daunting task, one that calls for innovation and cooperation across borders and industries. To make quantum computers a common part of our technology landscape, several significant breakthroughs are essential. First, we need to enhance the stability of quantum bits, often referred to as qubits. Unlike traditional bits that can simply be 0 or 1, qubits can exist in multiple states at once due to a property called superposition. This allows quantum computers to perform complex calculations much faster than their classical counterparts. However, qubits are extremely delicate and can lose their information quickly, which is known as decoherence. Finding ways to protect qubits from environmental interference and extending their lifetimes is crucial. Another important area is the error correction in quantum computing. Because qubits can easily be disrupted, we need sophisticated methods to detect and correct errors without losing the benefits of quantum computing. Current approaches to error correction are resource-intensive, meaning they use many more qubits than there are in the original computation. Streamlining this process will be vital in building more practical quantum systems. Scaling up the number of qubits is also necessary. Presently, most quantum computers have a limited number of qubits, which constrains their computational power. Researchers must develop new technologies and materials that allow for the fabrication of larger arrays of qubits that can operate together effectively. Integration with traditional computing technologies is another key aspect. For quantum computers to truly achieve mainstream adoption, they need to work alongside and complement the existing classical systems. This means creating hybrid models where classical and quantum computing tools can communicate and efficiently solve problems. Lastly, developing practical applications that benefit from quantum computing is essential. Industries such as pharmaceuticals, finance, and materials science are exploring how quantum computing can optimize processes and solve complex problems that are currently intractable. Demonstrating clear value in these applications will help convince businesses and governments to invest in this technology, pushing it toward mainstream use. Together, these breakthroughs will help us unlock the full potential of quantum computers and position them as an integral part of the technological fabric of our society. The prospect of consumer-grade quantum computers is an exciting topic in the world of technology. Right now, quantum computers exist in advanced laboratories and major tech companies. They operate using the principles of quantum mechanics, which allows them to process information in fundamentally new ways, significantly outperforming traditional computers for certain tasks. Imagine a standard computer processing information, like a person flipping through a book page by page. In contrast, a quantum computer can explore many pages at once, thanks to its reliance on quantum bits, or qubits, which can represent multiple states at the same time. This ability to perform numerous calculations simultaneously gives quantum computers the potential to solve complex problems much faster than current technology. As for whether these machines could reach consumer households, various hurdles must be addressed. One challenge is scalability. Making a quantum computer small and affordable enough for general use is no small feat. Moreover, quantum computers require specific conditions to function, such as extremely low temperatures to maintain qubit stability and protection from interference that could lead to errors in calculations. However, researchers and engineers are relentlessly innovating. Progress is being made to create more compact and accessible forms of quantum technology. Many believe it may take years or even decades, but the vision of having a quantum computer that fits on a desk and can be used for everyday tasks is not entirely out of reach. If achieved, this advancement could usher in a new era of computing, unlocking solutions for problems in various fields, from medicine to complex data processing. The journey to that future is underway, and while we aren't quite there yet, the fascination with quantum technology continues to grow. As quantum technology develops, several industries stand to gain significantly from its advancements. One of the first to come to mind is computing. Quantum computers operate on principles that allow them to process vast amounts of data and solve complex problems much faster than traditional computers. This means industries like finance, which rely on rapid calculations for risk assessment and algorithmic trading, will benefit immensely, enabling them to make better decisions in real time. Healthcare is another field poised for transformation. Quantum technology can enhance drug discovery processes by simulating molecular interactions with incredible accuracy. This could lead to the faster development of new medications, ultimately improving patient care and treatment options. Additionally, quantum imaging might revolutionize medical diagnostics, offering clearer and more detailed pictures of biological processes. Supply chain and logistics management could also see a major boost. Quantum algorithms can optimize routing and resource allocation far more effectively than current methods, potentially reducing costs and improving efficiency in transport and distribution networks. This would have a ripple effect on businesses reliant on timely delivery of products. Telecommunications and cybersecurity are also crucial sectors. Quantum communication offers advanced encryption methods that are nearly impossible to crack, which would greatly enhance data protection and privacy measures. This is particularly vital given the increasing amount of sensitive information being stored and transmitted digitally. Lastly, materials science stands to benefit as well. Quantum simulations can help scientists discover new materials with unique properties or improved efficiencies, opening doors for innovation across various applications, from energy storage to manufacturing. As quantum technology continues to advance, sectors such as computing, healthcare, supply chain management, telecommunications, and materials science will likely experience transformative changes that could redefine their operations and deliver substantial benefits. Quantum computing is a revolutionary technology that harnesses the strange principles of quantum mechanics to process information in ways that traditional computers cannot. At its core, a quantum computer uses quantum bits or qubits, which can exist in multiple states simultaneously, unlike classic bits that are either 0 or 1. This ability dramatically increases computational power and efficiency. When it comes to artificial intelligence and machine learning, quantum computing can significantly speed up tasks that involve vast amounts of data and complex calculations. Traditional algorithms used in machine learning may take a long time to find patterns or make predictions, especially with large datasets. However, quantum computers can analyze many possibilities at once, allowing certain computations to be done much faster. One of the key areas where quantum computing shines is optimization. Imagine trying to find the best solution among countless options, such as determining the most efficient route for deliveries in a city. For classical computers, this can be a lengthy process as they need to evaluate each option sequentially. In contrast, quantum computers can explore multiple routes simultaneously, making it much quicker to identify the optimal one. Moreover, quantum computing enhances machine learning through sophisticated algorithms that can learn from data more effectively. Techniques like quantum clustering and quantum feature selection allow these systems to improve their accuracy and efficiency in recognizing patterns. This means that applications like image and speech recognition could become even smarter and faster. Despite the potential, we are still in the early stages of this technology. There are obstacles to overcome, such as developing practical quantum hardware and refining algorithms for real-world applications. However, the collaboration between quantum computing, artificial intelligence, and machine learning holds great promise for creating systems that work faster, learn better, and solve complex problems that are currently beyond our reach. As we continue to unlock the potential of quantum computing, the synergy between these fields could lead us to breakthroughs that dramatically transform technology and society. Quantum-powered artificial intelligence has the potential to revolutionize the field by leveraging the unique properties of quantum mechanics. To understand this, consider how classical computers work. They process information using bits that can be either 0 or 1. This approach allows them to perform calculations sequentially, solving problems step by step. Now think about a quantum computer, which uses quantum bits or qubits. Unlike regular bits, qubits can exist in multiple states at once, thanks to a phenomenon called superposition. This means they can perform many calculations simultaneously. When applied to AI, this capability could enable quantum systems to analyze vast amounts of data at much greater speeds than classical systems can achieve. However, it's important to note that quantum AI isn't merely a stronger version of classical AI. It has different strengths that could be utilized for specific applications, particularly those some see as highly complex, such as optimization problems or simulating molecules, which are vital in drug discovery. While quantum AI could outperform classical AI in these areas, there are still many challenges to overcome. Research into quantum computing is ongoing, and practical implementations are still being developed. Classical AI currently has widespread applications and can handle numerous tasks efficiently. Therefore, While quantum-powered AI shows promise and may in some areas surpass classical systems in the future, it's not an immediate replacement. Instead, it may lead to a new era of AI that complements and enhances the existing technology rather than completely surpassing it. The journey of exploration in this intersection of quantum mechanics and artificial intelligence is just beginning, and the future holds exciting possibilities. Quantum mechanics plays a fascinating role in our understanding of the universe, and it may offer clues about dark matter, a mysterious substance that makes up a significant portion of the universe's total mass. While we cannot see dark matter directly because it does not emit light or other forms of electromagnetic radiation, scientists have inferred its existence through its gravitational effects on visible matter, such as galaxies and galaxy clusters. At the heart of quantum mechanics is the idea that particles behave in ways that can seem strange or counterintuitive. Instead of just being small spheres, particles can exist in multiple states or positions at once, a phenomenon known as superposition. This concept might suggest that dark matter could consist of unfamiliar particles that don't fit neatly into our current understanding of physics. Some theories propose that dark matter could be made of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact very weakly with ordinary matter, making them extremely hard to detect, yet they could explain the gravitational effects observed in the universe. Quantum mechanics could provide a framework to study these particles, exploring their properties and how they might behave under specific conditions. Additionally, experiments in quantum physics explore conditions like quantum entanglement, where particles become linked and influence each other regardless of distance. This could lead to new insights into dark matter's behavior and its role in the cosmos. As researchers continue to explore the relationship between quantum mechanics and dark matter, they are searching for answers in both particle physics experiments and astronomical observations. This pursuit may bridge gaps in our understanding and unlock the secrets of dark matter, revealing how it interacts with the universe in ways we have yet to imagine. Ultimately, while quantum mechanics might not provide all the answers, it serves as a vital tool that could help illuminate the hidden forces shaping our universe. Quantum tunneling is a fascinating phenomenon that occurs on a very small scale, one where the rules of classical physics no longer apply. Imagine a ball rolling towards a hill. If it doesn't have enough energy to climb over the hill, it simply rolls back. However, in the quantum world, particles can effectively tunnel through barriers, appearing on the other side without needing to go over the top. This happens because at this tiny scale, particles can exist in multiple states at once. This principle is not just an abstract idea, it has practical implications for future technology. For instance, quantum tunneling is key in the operation of devices like transistors, which are the building blocks of modern electronics. As technology progresses, we are pushing these devices to become smaller and more efficient. Quantum tunneling allows electrons to move through materials in ways that can lead to faster processing speeds and lower energy consumption. Looking further ahead, quantum tunneling could transform the field of quantum computing. Quantum computers have the potential to solve complex problems much faster than classical computers by leveraging the principles of quantum mechanics, including tunneling. They can conduct multiple calculations simultaneously, thanks to particles being able to exist in various states at once, and tunneling can facilitate this process, allowing faster transitions between qubits, the basic units of quantum information. Additionally, tunneling could influence advancements in medicine, such as in the development of new imaging technologies or targeted therapies that make use of quantum mechanics. The unique properties of quantum tunneling could enhance our ability to manipulate molecules at the atomic level, leading to breakthroughs in drug delivery systems or cancer treatment. Quantum tunneling is not just a curiosity of the quantum world, it is a bridge to the future of technology. By embracing this extraordinary phenomenon, we may unlock innovative solutions to current limitations, redefine how we compute, and even revolutionize healthcare. As we continue to explore the complexities of the quantum realm, the possibilities seem almost limitless. Quantum technology holds immense potential, but faces several significant hurdles before it can be widely adopted. One of the biggest challenges is the need for advanced infrastructure. Quantum systems often require extremely cold temperatures to function properly, which means powerful refrigeration systems. This added complexity makes it hard to integrate them into existing setups. Another barrier is related to the current understanding of quantum mechanics itself. The principles behind quantum technology are complex and not easily grasped, leading to a skills gap in the workforce. Training individuals who can develop, manage, and innovate in the realm of quantum technology is a substantial undertaking that takes time and resources. Moreover, there is the issue of error rates. Quantum computers are sensitive to their environments, and small disturbances can lead to significant errors. Developing techniques for error correction is critical, but it remains a difficult technical challenge. Until these systems can operate reliably, their practical use remains limited. Additionally, there's the matter of cost. The materials and technologies required to build quantum systems are often expensive. As a result, investing in quantum development can be a considerable financial burden for companies and institutions, which may discourage experimentation and innovation. Finally, there is a need for regulatory frameworks and standards. As quantum technology continues to develop, establishing guidelines and protocols will be essential for ensuring its safe and ethical use. Without these frameworks, it could be difficult to implement quantum technologies effectively across various sectors. While the prospects of quantum technology are exciting, overcoming issues related to infrastructure, skill development, error correction, cost, and regulation will be vital for its successful adoption. Each of these barriers requires careful attention and collective effort to advance into the next era of technology. Quantum advancements hold incredible potential for technology, potentially paving the way toward what some call a technological singularity. To grasp this idea, imagine that current technology is like a tool, enabling us to solve problems and communicate in ways that were once unimaginable. Now picture a scenario where we harness the principles of quantum mechanics, where particles can exist in multiple states at once or become linked across vast distances. This could revolutionize computing. Quantum computers, for instance, use these unique properties to process information at speeds far beyond our current capabilities. Instead of using bits that are either 0 or 1, quantum bits can represent both at the same time. This means they can tackle complex calculations like chemical simulations or large data analysis much faster than traditional machines. As quantum technology develops, it could lead to artificial intelligence that learns and adapts at unprecedented rates. Imagine machines that can create new algorithms and systems without human assistance. This acceleration could produce innovations that outstrip our ability to understand or control them, leading to a point in time where change occurs at an exponential rate, the essence of a technological singularity. However, reaching this point is not just about technological advancements. It raises questions about ethics, safety, and the very nature of intelligence. The impact of such rapid progress on society, jobs, and daily life would be profound. While quantum advancements may bring us closer to this singularity, they also require careful handling to ensure they benefit humanity and do not spiral out of control. To consider whether quantum computers will one day be as common as smartphones, we must first understand the nature of both technologies. Smartphones have become a vital part of our daily lives because they are accessible, user-friendly, and designed for a wide range of tasks, from communication to entertainment. They integrate seamlessly into everyday activities, making them essential. Quantum computers, on the other hand, operate on principles that differ from traditional computers. These devices harness the peculiar behavior of tiny particles to process information in ways that standard computers cannot. They can solve certain problems significantly faster, especially those involving vast amounts of data or complex calculations, like drug discovery or optimizing logistics. However, the technology is still in its infancy. Current quantum computers are often large, expensive, and require intricate conditions to function properly, such as extremely low temperatures. They are primarily tools for researchers and scientists aimed at solving specific problems rather than general-purpose devices for the public. For quantum computers to rival smartphones in prevalence, several key developments are needed. First, they must become more accessible, meaning that they need to be smaller, more affordable, and capable of functioning in everyday environments. Second, software and application ecosystems must grow to match these machines' unique capabilities, allowing average users to see practical benefits in their lives. If these advancements occur, we could see quantum computers becoming as common as smartphones in the future. But this may take years, if not decades, as the technology matures. So while it is possible, the journey from scientific innovation to everyday device is long and complex. Quantum mechanics offers a fascinating peek into the very nature of reality, suggesting that at its core, the universe is both strange and unpredictable. Imagine the tiniest particles, which make up everything around us, behaving in ways that seem impossible by everyday standards. For instance, these particles can exist in multiple states or locations at once, similar to a person being in two places at the same time. This idea, referred to as superposition, flips our typical understanding of separate objects on its head. When we observe these particles, they behave differently, as if the act of looking changes them. This notion hints at a peculiar relationship between observers and what is observed, suggesting that there is an interconnectedness within the fabric of reality. In a way, quantum mechanics reveals that what we perceive as solid and certain is, in fact, influenced by our own interactions. Moreover, particles can become entangled, meaning they share a connection that transcends distance. Imagine two dancers performing a duet where the movements of one instantly influence the other, no matter how far apart they are. This phenomenon challenges our conventional ideas about information and influence, pointing to a reality that is far more interconnected and complex than it first appears. As we delve deeper into the quantum world, the very definitions of reality, certainty, and causality begin to blur. Instead of a straightforward narrative, quantum mechanics portrays a universe full of potential, where possibilities exist until they are selected by interaction. This strange yet captivating perspective invites us to reconsider what we think we know about the nature of existence itself. Reality, it seems, is not just a backdrop for events, but a dynamic interplay that continuously shapes and reshapes our understanding of the cosmos. The idea that the universe could function as a giant quantum computer is both fascinating and complex. At its core, this concept suggests that the fundamental workings of our universe might mirror the principles of quantum computing. To break this down, let's think about what quantum computers do. They take advantage of the strange behavior of tiny particles, which can exist in multiple states at once and interact in ways that classical computers cannot. Now, consider the universe as a whole. Some scientists propose that every particle, every interaction, and every event involves quantum properties, similar to how a quantum computer processes information. In this view, the universe may be seen as a vast network of quantum bits or qubits, which are the building blocks of quantum information. While classical bits are either 0 or 1, qubits can be both at the same time, leading to immense processing power. If the universe operates on these principles, it implies that it computes or processes information at a cosmic scale, influencing everything from the formation of galaxies to the behavior of atoms. This idea leads to questions about the nature of reality itself. Are our experiences and perceptions merely quantum computations unfolding in a massive interconnected system? However, it's important to clarify that this is still a theoretical notion. We are yet to fully understand how quantum mechanics applies on a universal scale and whether it truly manifests the capabilities of computing. The relationship between quantum physics and the fabric of reality remains one of the most intriguing puzzles in science, inviting us to rethink not only our understanding of computation, but also the universe as a whole. The intersection of quantum mechanics and consciousness theories is a captivating area of exploration that raises important questions about the nature of reality and awareness. Quantum mechanics is the branch of physics that describes the behavior of the very small, like atoms and subatomic particles. It tells us that at such tiny scales, particles can be in multiple states at once, a concept known as superposition. This means they're not confined to a single location or state until they're measured or observed. Now, when we consider consciousness, we touch upon one of the most profound mysteries in science. Consciousness is our subjective experience, our ability to perceive and respond to the world around us. Some theories suggest that consciousness itself may influence the behavior of quantum particles, a notion that straddles science and philosophy. One idea is that consciousness might play a role in collapsing that superposition state into a single outcome. The act of observation could potentially impact the quantum system. Much like a photographer capturing a moment, before the click, the scene holds multiple possibilities, but afterward, there's only one image. This leads to the captivating hypothesis that consciousness is not just a byproduct of our brain, but could be intricately linked to the fundamental fabric of reality. However, it's essential to approach these ideas with caution. The relationship between quantum mechanics and consciousness remains largely speculative. Many scientists argue that while our understanding of quantum phenomena is still incomplete, there is currently no solid evidence to definitively link the two. Instead, these ideas challenge us to think about existence and perception in entirely new ways. As we continue to explore both the depths of quantum mechanics and the enigma of consciousness, we may uncover insights that not only shake the foundations of science, but also reshape our understanding of what it means to be aware in an incomprehensibly vast universe. The journey of these intertwined fields invites us to engage with the mysteries that lie at the heart of existence itself. Quantum mechanics introduces fascinating ideas about the behavior of particles at the smallest scales, often leading to discussions about the bigger questions in life, including free will. At its core, quantum mechanics suggests that, unlike larger objects that follow predictable paths, particles can exist in multiple states at once until they are observed. This has led some to wonder if these behaviors could somehow relate to human decision-making and the sense of free will. Imagine throwing a coin into the air. In classical mechanics, the outcome of whether it lands on heads or tails can be determined if you know the precise conditions of the throw. In contrast, quantum mechanics tells us that until you observe the result, the coin can be in a state of both heads and tails simultaneously. This uncertainty creates flexibility. If we liken our decisions to the behavior of quantum particles, could it mean that our choices are not set until we act on them? However, linking quantum mechanics to free will is complex and often controversial. Many scientists and philosophers argue that while quantum events are unpredictable, they do not necessarily grant our minds the agency we think we have. After all, human behavior is influenced by countless factors, including biology, culture, and personal experiences. So, while quantum mechanics challenges traditional views of determinism, that everything happens for a specific reason, it doesn't straightforwardly provide evidence for free will. Ultimately, the relationship between quantum mechanics and free will remains a topic of rich debate. It opens the door to intriguing ideas but does not offer a definitive answer. Exploring this intersection encourages us to think deeply about what it means to make choices in a universe where certainty and randomness coexist. Quantum uncertainty introduces fascinating twists to our understanding of time. At the very small scale of particles like electrons, things do not follow the clear paths we are used to observing. Imagine trying to pinpoint the exact location and speed of a moving car. The harder you try to measure its speed, the less accurately you can tell where it is at that moment, and vice versa. This is the essence of quantum uncertainty. In this realm, time becomes less of a steady linear path and more like a fluid concept. Events do not unfold in a strictly ordered manner like frames in a movie. They are interconnected. As particles exist in multiple states until they are observed, this leads to a more complex picture where past, present, and future become interlinked. Additionally, some theories suggest that time itself might not be a fundamental part of the universe at very small scales. Instead, it could emerge from more basic quantum interactions. This challenges our conventional view of time as a constant. If time can be influenced by these unpredictable quantum states, it opens up new questions about causality and the very nature of reality. Thus, quantum uncertainty doesn't just shake our beliefs about particles. It also invites us to rethink how we perceive time itself. It suggests that there may be layers to time we have yet to explore, where our usual understanding falls short, leading us to a mysterious frontier rich with possibilities. Quantum mechanics and multiverse theory are deeply intertwined in the realm of modern physics. To understand this connection, we first need to grasp what quantum mechanics entails. This branch of physics describes the behavior of very small particles such as atoms and subatomic elements. In quantum mechanics, particles can exist in multiple states or locations at once until they are observed or measured. This phenomenon is often called superposition. Now, let's explore multiverse theory, which suggests that there may be multiple, perhaps infinite universes existing parallel to our own. In this framework, each universe could have different outcomes or realities resulting from various initial conditions. The link between quantum mechanics and multiverse theory emerges from a specific interpretation of quantum mechanics known as the many worlds interpretation. According to this viewpoint, every time a quantum event occurs, such as a particle being in two states at once, the universe splits into multiple branches. Each possible outcome happens in its own separate universe. Therefore, if you were to make a decision, let's say to turn left or right, one universe would see you going left, while another sees you going right. This idea challenges traditional perceptions of reality and has profound implications for our understanding of existence. It suggests that every choice and randomness in quantum events could lead to the creation of numerous worlds, each reflecting different histories and possibilities. While these concepts are still theoretical and heavily debated among physicists, they open fascinating avenues for exploring the nature of reality itself. Quantum fluctuations are fascinating phenomena that occur at the smallest scales of the universe, where the laws of quantum mechanics play a dominant role. Imagine the fabric of space-time as a vast and stretchy web, where every point can vibrate and fluctuate in a way that we don't observe in our everyday lives. In this tiny world, energy does not remain constant. Instead, it jumps in and out of existence. These fluctuations arise from the uncertainty principle, which tells us that we cannot precisely know both the position and momentum of a particle at the same time. This allows particles to appear momentarily from the vacuum of space, only to vanish again almost instantly. Although these particles are fleeting, their effects can resonate throughout space-time. As they pop in and out of existence, quantum fluctuations contribute to energy variations in the vacuum. This means that even seemingly empty space is alive with activity, constantly buzzing with these brief energetic bursts. Think of it as a dense fog within which the very essence of reality is being shaken and stirred. On a grander scale, these fluctuations influence the structure of space-time itself. They are believed to play a crucial role in cosmic events, such as the birth of the universe during the Big Bang. In moments of extreme expansion, tiny fluctuations could have sown the seeds for the uneven distribution of matter that would later form galaxies and galaxy clusters. Furthermore, in regions of intense gravitational forces, like near black holes, the effects of quantum fluctuations are heightened, potentially creating ripple effects that affect even light. Thus, at the intersection of quantum mechanics and general relativity, these tiny events at the quantum level become vital players in shaping the universe as we experience it. Quantum fluctuations are the subtle twitches and shudders of space-time, influencing cosmic phenomena and contributing to the very structure of reality, reminding us that the universe is a place of constant motion, even in the quietest corners of its vastness. Quantum effects, though often associated with the tiny world of subatomic particles, can indeed influence our larger macroscopic reality, though the mechanisms are subtle and fascinating. At the quantum level, particles exist in states of probability rather than certainty. This means they can behave in strange ways, like being in multiple places at once or taking multiple paths simultaneously. These quirky behaviors seem to fade away as we look at larger scales where objects behave more predictably. However, there are instances where quantum phenomena have a noticeable impact in the macroscopic world. For example, take the process of photosynthesis in plants. Within the chlorophyll molecules, energy transfer happens through quantum coherence, allowing plants to capture sunlight efficiently. This means that the unique properties of quantum mechanics allow plants to harness energy in a way that would be less effective if they behaved solely according to classical physics. Another intriguing case is superconductivity. In certain materials at extremely low temperatures, electrical resistance can drop to zero. This state arises from Cooper pairs, where electrons behave collectively in a way that only quantum mechanics can fully explain. This phenomenon defies our everyday experiences, demonstrating how quantum properties can result in effects we see in the larger realm. Similarly, phenomena like quantum entanglement have sparked research into applications such as quantum computing and secure communication. These technologies hold the potential to revolutionize how we process and transmit information, deriving benefits from quantum effects that transcend the microscopic scale. So while quantum behavior seems to fade into the background as we zoom out to larger objects, it quietly underpins processes and technologies in our everyday lives, illustrating a remarkable connection between the tiniest particles and the vast world around us. The observer effect is a fascinating concept rooted in quantum mechanics, where simply observing a phenomenon can change its state. This means that when scientists measure or look at certain tiny particles, such as electrons, those particles behave differently than they do when they are not being observed. To illustrate, think of a game of hide and seek. The act of looking for someone can change their hiding behavior. However, it is important to clarify that the observer effect does not imply that consciousness itself has a direct influence on reality. Instead, it suggests that the act of measurement or observation, regardless of who or what is doing the observing, plays a crucial role in determining how quantum particles behave. This doesn't require consciousness, it only requires interaction with the measuring instruments. Many people find this idea intriguing, leading to philosophical questions about the nature of reality and consciousness. While the observer effect indicates that observation and measurement are significant in the quantum realm, it remains a scientific phenomenon rather than a direct link between consciousness and the fabric of reality. Science continues to explore these relationships, but as of now, we understand that observation transforms the situation without asserting that our awareness shapes the universe itself. Quantum indeterminacy raises intriguing philosophical questions about the nature of reality and our understanding of free will. At its core, this concept suggests that not everything in the universe is predetermined, rather certain outcomes are probabilistic. Imagine rolling a die. You can't know for sure which number will land face up until you actually roll it, even though you can calculate the chances of each outcome. Similarly, in the quantum realm, particles exist in multiple states at once until they are observed, at which point they choose a specific state. This uncertainty calls into question traditional views of causality, which holds that every effect has a specific cause. If fundamental events can occur without a particular cause, it challenges our understanding of how events unfold in the universe. It pushes us to reconsider how we define reality. Is the act of observation itself giving shape to existence? In other words, does the universe require consciousness to manifest certain outcomes? Moreover, quantum indeterminacy intersects with discussions about free will. If particles behave in unpredictable ways, could human choices too be inherently unpredictable? Some philosophers suggest this unpredictability might offer a framework for true free will, while others contend that randomness does not equate to freedom. Ultimately, the implications of quantum indeterminacy stretch into the realms of ethics, knowledge, and metaphysics. It compels us to confront the limits of our understanding and encourages a more nuanced worldview, where certainty and predictability are perhaps not the bedrock of reality we once thought. This shift invites a deeper exploration of how we engage with existence itself and the mysteries that lie within. Quantum physics plays a vital role in our understanding of the Big Bang, which is the event that marks the beginning of our universe. To grasp this connection, we start by recognizing that the early universe was a hot, dense point where all matter and energy were crammed closely together. In this environment, the laws of quantum physics come into play, especially concepts such as uncertainty and wave-particle duality. Imagine this initial state as a bubbling cauldron of energy. Quantum fluctuations, tiny random changes in energy occurring at an incredibly small scale, were present even before the Big Bang itself. These fluctuations contributed to the differences in density throughout the universe. When the Big Bang occurred, it wasn't just an explosion, it was a rapid expansion of space itself, driving matter and energy outward. As the universe expanded, quantum effects helped shape how particles formed and interacted. For instance, energy could transform into different types of particles, as dictated by the rules of quantum mechanics. This transformation set the stage for the formation of protons and neutrons, the building blocks of atoms. Following the initial moments, as the universe cooled, these particles began to combine into hydrogen and helium. This process of formation is rooted in quantum interactions. The patterns of attraction and repulsion guided by quantum physics helped establish the early structure of the universe. Overall, while classical physics explains many observable phenomena of the universe, it is the principles of quantum physics that provide a deeper understanding of the very beginning, revealing how our universe emerged from a singular state and evolved into the vast expanse we see today. In this light, quantum physics not only aids our understanding of the Big Bang, but also illustrates the fundamental nature of reality itself. Quantum mechanics, the fascinating branch of physics that examines how the very small particles of the universe behave, holds potential keys to understanding black holes. At first, black holes seem to clash with quantum principles. In simple terms, they are regions of space where gravity is so strong that not even light can escape. This creates a puzzle because, according to quantum mechanics, information about what falls into a black hole should not just disappear. Scientists have proposed that quantum effects could help us unlock this mystery. One idea involves something called information preservation. This concept argues that every particle carries information about its state, and even if something falls into a black hole, that information does not vanish. Instead, it might become spread out across the black hole's event horizon, the boundary beyond which nothing can escape. Another fascinating idea is Hawking radiation, named after the physicist Stephen Hawking. He theorized that black holes can emit radiation due to quantum effects near their event horizon. This suggests that black holes are not entirely black, but can evolve and eventually evaporate over very long timescales. As they lose energy, they could potentially release the information they contained back into the universe in a different form. Ultimately, merging quantum mechanics with general relativity, the theory that describes gravity, may give us deeper insights into the nature of black holes. This journey could change our understanding of the universe, suggesting that black holes might not be the final destinations we once thought, but instead connected to a larger cosmic story. This intersection of ideas is an exciting frontier for scientists, drawing them closer to deciphering the mysteries surrounding these enigmatic structures in the cosmos. Cosmic inflation refers to a period of rapid expansion of the universe that occurred just after the Big Bang. During this brief moment, the universe grew immensely, much faster than the speed of light. At the heart of this phenomenon are quantum fluctuations, which are small, random changes that occur at the very smallest scales of energy and matter. Imagine the fabric of the universe as a calm surface of water. When a stone is dropped into it, ripples move outward in all directions. Quantum fluctuations are like those tiny disturbances, creating temporary pockets of energy in the universe even when it seems empty. These fluctuations can happen anywhere in space, and they play a crucial role during inflation. As inflation occurs, these tiny ripples get stretched out along with the expanding universe. This means that regions of space that were once incredibly small become vastly enlarged. As a result, these fluctuations lead to uneven distribution of energy throughout the cosmos. This unevenness is essential because it seeds the formation of galaxies and other structures we observe today. In simpler terms, you can think of these quantum fluctuations as tiny seeds planted in a balloon that is rapidly inflating. Each bump and crease formed during this rapid growth creates variations, which later blossom into the clusters of galaxies we see scattered across the universe. Thus, quantum fluctuations serve as the foundational building blocks of the structure of the universe, shaping the cosmos as we know it. Quantum theory and string theory are both important frameworks in understanding the universe, but they operate on different scales and concepts. Quantum theory measures the smallest particles and their interactions, providing a framework to explain how everything from atoms to subatomic particles behave. It reveals that particles can exist in multiple states at once, and that their properties are fundamentally unpredictable until they are observed. String theory, on the other hand, takes these particles as the building blocks of the universe and describes them as tiny vibrating strings. Imagine if every elementary particle was not just a point, but rather a tiny string, similar to a guitar string, whose vibrations determine what kind of particle it is. Like different notes from a string produce different sounds. This theory aims to unify all fundamental forces of nature, including gravity, under a single framework, seeking to bridge the gaps between quantum physics and general relativity, which describes gravity's effect on large objects. The relationship between these two theories arises in efforts to understand how gravity operates at the quantum level. While quantum theory treats gravity separately, string theory proposes a way to incorporate it. This leads to concepts like extra dimensions beyond the familiar 3 dimensions we know, providing a richer and deeper understanding of the fabric of our universe. Quantum theory lays the groundwork for what these microscopic particles are and how they behave, while string theory attempts to build a more encompassing theory that includes gravity and potentially everything else in the universe. Together, they push the boundaries of what we know about the universe and provide paths for future discoveries. If we could fully control quantum gravity, the implications would be astounding and could redefine our understanding of the universe. Quantum gravity attempts to merge quantum mechanics, which governs the very small, with general relativity, which explains the behavior of massive objects like planets and stars. Right now, these two theories stand apart without a common framework. Imagine having the ability to manipulate the fabric of space-time itself. This means we could potentially influence how gravity behaves on a quantum level, leading to technologies and phenomena that we can only dream of today. For example, controlling quantum gravity might allow us to create stable wormholes, which could serve as shortcuts through space, making interstellar travel far faster than current methods allow. Energy manipulation could also become a reality. By harnessing the effects of quantum gravity, we could tap into powerful new energy sources, possibly leading to clean energy, or even the ability to control black holes, using their unique gravitational properties for energy production, rather than risk. Furthermore, mastering quantum gravity could lead to advancements in how we understand and predict cosmic events. It would strengthen our grasp of phenomena like the very early universe, black holes, and perhaps even the nature of dark matter and dark energy, which comprise a significant portion of the universe yet remain elusive. One of the most intriguing prospects involves the impact on human consciousness and reality. With such control, we might further explore the intersections of physical and metaphysical realms, potentially delving into questions about existence and the universe in ways we have not yet considered. Overall, mastering quantum gravity would not only revolutionize technology and science, but could also change our fundamental understanding of reality itself, opening doors to realms previously reserved for speculation and science fiction. A quantum understanding of reality could indeed revolutionize the way we approach space travel. At its core, quantum mechanics describes the behaviors of tiny particles like atoms and photons that make up everything in the universe. One of the most intriguing aspects of quantum physics is the idea of superposition, where particles exist in multiple states at once. This concept could inspire new propulsion systems that allow spacecraft to explore multiple pathways or possibilities simultaneously, leading to faster and more efficient travel. Moreover, quantum entanglement is a phenomenon where particles become interconnected no matter the distance separating them. Imagine being able to communicate instantly with a spacecraft far away through a quantum connection. This could provide immense advantages for navigation and coordination without interference from the vast distances that typically cause delays in communication. Additionally, harnessing quantum properties might help in developing advanced technologies for energy generation. For instance, advancements in understanding quantum behaviors could lead to breakthroughs in harnessing energy from the vacuum of space itself, offering almost limitless power supplies for deep space missions. Combining these quantum principles with traditional space travel methods could lead to innovative designs, such as more efficient thrusters, or even theoretical ideas like the use of wormholes for near-instantaneous travel. While we are still on the cusp of fully uncovering the implications of quantum mechanics, its potential to reshape our understanding of reality, and by extension, our capabilities in space travel, is truly exhilarating. Time travel, while a fascinating concept, dwells within the realm of theoretical physics and quantum mechanics, offers intriguing pathways for exploration. According to some interpretations of quantum mechanics, time is not as linear as it seems. Rather, it can twist and turn in ways that challenge our everyday understanding. One theory suggests the existence of parallel universes. Imagine every decision you make creating a branching path into a different version of reality. If time travel were possible, it may not mean returning to the past in the same timeline, but instead entering a new universe where events have unfolded differently. This implies that any attempt to change the past wouldn't affect your original timeline, but would give rise to a completely different one. Additionally, certain solutions to the equations of general relativity, like wormholes, hint at ways to connect different points in time, similar to how they connect distant locations in space. Wormholes could theoretically allow one to travel back or forward in time, but they also come with enormous challenges. For example, Maintaining a stable wormhole may require unseen forms of matter or energy that we have yet to discover. Another consideration is the concept of closed time-like curves, which refer to paths in spacetime that return to their starting point. Some physicists argue that at the quantum level, particles may exhibit behaviors that allow for such loops, though translating these ideas to macroscopic objects like humans remains purely speculative. While quantum mechanics opens the door to fascinating possibilities about time travel, many complexities and paradoxes arise, including questions about causality. This concept deals with cause and effect, and time travel could lead to situations where an action in the past could alter the future in unexpected ways. Overall, while the theories are tantalizing, actual time travel remains firmly in the theoretical domain, requiring advancements in our understanding of physics and reality. Quantum effects play a fundamental role in shaping the structure of our universe, even on the grandest scales. At the heart of this concept is the idea that everything in the universe, from the smallest particles to vast galaxies, experiences forces and rules dictated by quantum mechanics. This branch of physics examines the behavior of matter and energy at extremely small scales, where traditional ideas about how things work begin to break down. One of the most profound influences of quantum mechanics is seen in the early moments of the universe, just after the Big Bang. During this incredibly hot and dense period, tiny fluctuations at the quantum level gave rise to variations in density. Imagine a calm pond suddenly disturbed by a small pebble thrown into it. Those ripples can lead to bigger waves. Similarly, these tiny fluctuations set off a chain of events that influenced how matter began to clump together, ultimately leading to the formation of galaxies and large-scale structures we see today. Additionally, quantum mechanics introduces the concept of superposition, where particles can exist in multiple states simultaneously until they are observed. This principle suggests that the early universe didn't just settle into a single formation, but rather a range of possibilities. These possibilities collapsed into specific outcomes as structures formed, leading to the diverse cosmos we observe. Another significant aspect is the phenomenon of entanglement, where particles become linked in ways that transcend distance. Even if two particles are light years apart, a change in one will instantaneously affect the other. This interconnectedness may suggest that the fabric of the universe is more unified than it appears, and can influence the formation and behavior of galaxies and cosmic structures. Moreover, the behavior of fundamental particles, governed by quantum principles, sets the stage for how elements interacted after the Big Bang. The creation of the first atoms led to the birth of stars. These stars then formed galaxies, shaping the larger structures throughout the universe, driven by yet more quantum interactions at every stage. Quantum effects are not merely tiny ripples in the fabric of the cosmos, they are foundational to how reality itself is structured. They influence everything from the birth of stars to the large-scale arrangement of galaxies, thus playing a critical role in defining the universe as we know it. Quantum physics opens a fascinating door to the possibility of other dimensions. To understand this, let's start by imagining our everyday experience. We live in a world with 3 dimensions of space: length, width, and height. However, scientists, particularly those studying string theory, propose that there could be many more dimensions beyond these familiar 3. String theory suggests that the fundamental particles we see, like electrons and quarks, aren't just tiny points. Instead, they may be tiny strings vibrating at different frequencies. This concept leads to the idea that these additional dimensions could become apparent when we explore the inner workings of these strings. In a way, the higher dimensions are compact and curled up so tightly that we don't notice them in our normal lives. In quantum physics, particles behave in peculiar ways, leading to what we call quantum entanglement. This phenomenon shows that particles can be connected to one another in ways that defy our traditional understanding of space and time. These connections hint at deeper layers of reality, where the rules differ from our common experiences. Some theorists believe that these strange behaviors could imply the existence of additional dimensions, which might provide pathways between distant points in our universe. Moreover, advanced experiments, like those conducted at particle accelerators, seek to uncover more about the fundamental forces of nature. These investigations could reveal signs of extra dimensions, possibly through unusual patterns in particle collisions or energy levels. If these extra dimensions do exist, they may provide insights into some of the greatest mysteries of the universe, such as dark energy and the nature of gravity itself. While quantum physics does not explicitly confirm the existence of other dimensions, it provides the framework and intriguing possibilities for their exploration. As science progresses, it challenges our understanding and might one day unveil layers of reality beyond our current perception. Quantum physics has profoundly changed our understanding of the universe, yet it presents mysteries that continue to puzzle scientists. One of the most striking questions revolves around the nature of quantum mechanics itself. While scientists can predict how particles behave, the underlying reason why they behave that way remains elusive. We often see particles existing in multiple states at once, but it is unclear what causes them to choose a definite state when observed. This phenomenon is known as wave function collapse, challenging our conventional understanding of reality. Another captivating question is about entanglement, which occurs when particles become interconnected such that the state of one instantly influences the state of another, no matter how far apart they are. This defies our intuitive grasp of space and locality, leading to inquiries about how information is transferred and whether it implies faster-than-light communication, something currently deemed impossible by the theory of relativity. Additionally, a pressing question in quantum physics is how to reconcile it with gravity. Quantum mechanics successfully describes the behavior of small particles, while general relativity explains gravity on a large scale. However, these two frameworks clash in extreme situations, such as the centers of black holes or the conditions of the Big Bang. Finding a unified theory that encompasses both quantum mechanics and gravity remains an ongoing quest and one of the biggest challenges in modern physics. Furthermore, scientists are investigating the implications of quantum theories on the fabric of reality. Concepts like many worlds suggest that every decision creates multiple parallel realities. However, the existence of these alternate timelines remains contentious and unproven. Each unanswered question opens the door to deep exploration, and as our understanding of quantum physics evolves, so too may our answers. The connection between quantum physics and consciousness is a fascinating area of exploration. At its core, consciousness refers to our awareness and understanding of ourselves and the world around us. Quantum physics, meanwhile, is the study of the smallest particles that make up matter and energy, revealing their strange and counterintuitive behavior. Some researchers propose that the principles of quantum mechanics might shed light on how consciousness arises. They point to phenomena like superposition, where a particle can exist in multiple states at once, suggesting the brain could also process information in ways that traditional models might not capture. It's as if the mind could be likened to a quantum computer, performing complex calculations simultaneously rather than sequentially. Another quantum concept is entanglement, where particles become intertwined in such a way that the state of one can instantly influence the state of another, no matter the distance between them. This raises intriguing possibilities about interconnectedness, possibly hinting at how individual consciousness might relate to a broader collective awareness. However, it's essential to note that these ideas remain largely speculative. The intersection of quantum physics and consciousness is still a topic of debate among scientists. While some theorists believe that quantum processes could contribute to the workings of the mind, mainstream neuroscience primarily views consciousness as a product of biological processes and brain activity. In the end, while quantum mechanics presents compelling frameworks for understanding complex systems, including the brain, much more research is needed to draw solid conclusions about how, or if, it truly relates to the mystery of consciousness. This captivating exploration may unveil new dimensions of understanding what it means to be aware. The universe is indeed thought to operate on principles that echo those found in quantum systems, inviting a fascinating connection between the cosmos and quantum mechanics. Quantum systems are characterized by phenomena that seem strange and counterintuitive, like particles existing in multiple states at once or behaving like both particles and waves. When we look at the universe, especially at its very origins and components, we see these quantum principles at play. At the very beginning of the universe, during an epoch referred to as the Big Bang, conditions were so hot and dense that classical physics could not adequately describe what was happening. Instead, quantum mechanics took the lead in explaining how the fundamental particles interacted, forming the building blocks of everything we see today. Moreover, the universe is a vast, interconnected entity where tiny quantum particles can influence one another over incredible distances through a phenomenon called entanglement. This peculiarity implies that what happens to one particle can instantaneously affect another, regardless of the space between them. It gives rise to questions about the nature of reality and how particles communicate across the vastness of space. Another captivating aspect is superposition, where particles can exist in multiple states until observed. This principle raises intriguing possibilities about the universe's structure and our understanding of reality itself, challenging the way we perceive existence. Overall, while the universe operates on a grand scale, the underlying mechanics often resemble those found in quantum systems, suggesting a deep connection between the incredibly small and the vastly large. Scientists are still uncovering the mysteries of this interplay, hoping to achieve a more unified theory that bridges the gap between quantum mechanics and the forces that govern the cosmos as a whole. This pursuit brings us closer to understanding not just the universe, but also our place in it. The delayed choice quantum eraser experiment is a fascinating study in quantum mechanics that challenges our understanding of reality and observation. Imagine a scenario where light particles, called photons, can behave like both particles and waves. The classic double-slit experiment shows this duality beautifully. When photons pass through two slits, they create an interference pattern on a screen, suggesting they are behaving like waves that spread out and overlap. Now, in the delayed choice quantum eraser experiment, scientists complicate this setup. After the photons have passed through the slits and hit the screen, they can introduce additional equipment that decides whether or not to erase the information about which slit each photon went through. This decision can take place even after the photons have already been detected. Astonishingly, if scientists decide to erase this which path information, the interference pattern re-emerges, as if the photons decided to behave like waves all along. This indicates that the behavior of photons doesn't just depend on how they travel through space, but also on whether or not we choose to gather information about their journey after the fact. The results of this experiment lead to one of the most mind-boggling conclusions in quantum physics. The act of measurement can influence outcomes retroactively. This reveals deep insights about causality and the nature of reality, raising questions about how observation itself shapes the world around us. It demonstrates that in the quantum realm, reality is not always as straightforward as it seems, merging aspects of time, observation, and fundamental physics in ways that challenge our typical understanding of cause and effect. The idea that our reality could be a simulation is a fascinating concept that stretches beyond science into philosophy. It suggests that everything we experience could be part of an advanced computer program, much like a virtual reality game. When we look at quantum mechanics, the science that explains the behavior of the smallest particles in the universe, there are intriguing elements that could support this theory. At its core, quantum mechanics reveals strange behaviors. For example, particles can exist in multiple states at once until they are observed. This has led some theorists to propose that reality needs a player to define its state, much like a simulation that only renders visuals when someone looks at them. This phenomenon, often illustrated by the thought experiment of Schrödinger's cat, challenges our understanding of what is real and activated by observation. Moreover, quantum entanglement illustrates how particles can be interconnected regardless of distance, leading to the idea that information could be shared instantaneously, similar to data being transferred in a computer network. If our universe operated similarly, it could imply an underlying code or structure governing the laws of physics. However, the idea that our entire reality is a simulation remains speculative. While quantum mechanics introduces questions about the nature of existence, it's essential to understand that these theories are still being explored and debated within the scientific community. The question of whether our reality is a simulation encourages us to look deeper into the nature of consciousness, existence, and the universe itself, inviting us on a journey of exploration where science, philosophy, and imagination intersect. Quantum physics offers a fascinating perspective on the arrow of time, which refers to the one-directional flow of time we experience. In everyday life, we notice events unfolding in a specific order, like a glass shattering before it magically reassembles. This observation hints at the concept of time moving from the past into the future. At the core of quantum physics is a principle called superposition. This means that, at a fundamental level, particles can exist in multiple states or places at once until something measures or observes them. When a measurement occurs, the particle collapses into one unique state. This process is fundamentally tied to time. The arrow of time is closely connected to another essential idea known as entropy, which is a measure of disorder or randomness in a system. In practical terms, systems tend to evolve from order to disorder. For example, an unkempt room naturally becomes messier over time if not tidied up. This shift towards increased disorder represents the second law of thermodynamics and establishes a direction for time. When we talk about the arrow of time, we often refer to this increase in entropy. Interestingly, quantum physics introduces scenarios where time does not follow our usual expectations. For example, in certain quantum experiments, systems can behave in ways that defy the classical understanding of time's flow. Yet, regardless of these complexities, our experience remains consistent. We perceive time passing from moments of greater order to those of more chaos. The intersection of quantum mechanics and the arrow of time sheds light on the underlying dynamics of our universe and the nature of reality itself. Quantum physics introduces us to a realm where the behavior of tiny particles defies our everyday understanding of reality, opening the door to a concept often described as infinite possibilities. Imagine the world of atoms and subatomic particles acting like dice. When we observe these particles, they do not just settle into one outcome. Instead, they can be in many states at once until we measure them. This phenomenon is known as superposition. Consider a simple example using a famous thought experiment about a cat. A cat can be both alive and dead simultaneously as long as we don't observe it. Once we peek into the box, we force the cat into one reality, alive or dead. This suggests that until something is observed, it exists in multiple states, leading to countless potential outcomes. Now, relating this back to the universe around us, quantum physics posits that every particle we interact with exists in a sea of probabilities. Each choice made, each interaction that occurs, creates branches of new possibilities. This web of potential outcomes expands infinitely, leading to the idea of parallel realities or universes, where each decision could lead to a different path. Thus, in the quantum world, the concept of infinite possibilities is not just a philosophical notion, but a fundamental characteristic of how nature operates at the smallest scales. As scientists explore these ideas further, they try to understand implications for everything from computing to understanding the nature of reality itself. The true magic of quantum physics lies in this ability to embrace uncertainty and the extraordinary potential that comes from it, making us rethink the nature of existence beyond the linear paths we are used to. Each moment, each interaction is a chance for the universe to unfold in myriad ways, hinting at a much richer tapestry of reality. The idea that reality could be made of quantum information instead of traditional matter is a fascinating concept. Think of quantum information as the fundamental building blocks of everything around us, similar to how tiny Lego pieces can construct large structures. In quantum mechanics, information is encoded in the properties of quantum particles, such as their position and spin. Imagine that our universe operates like a complex computer program. Instead of physical objects being the core essence of reality, it suggests that the true nature of everything is digital information at its very lowest level. Just like how information can represent various forms, like text, images, or sounds, quantum information can describe the state of particles, energy, and even the forces that connect them. This perspective aligns with the idea that when you dig deep into the fabric of reality, what you find may not be solid objects, but rather a network of relationships and interactions that define the behavior of particles. This raises compelling questions about how perception, consciousness, and the universe itself are intertwined. If reality is eventually built from information, understanding these interactions could change how we perceive existence. Moreover, some scientists and theorists are exploring concepts like holography, proposing that all the information in a three-dimensional space can be represented as a two-dimensional surface. This leads to a new way of thinking about gravity, black holes, and the nature of the cosmos. It hints at a universe where what we see and feel is just the manifestation of deeper, unseen information processes. If reality is indeed made of quantum information, it means the universe functions on principles that may have more to do with understanding connections and relationships rather than just solid matter. This could open new doors to exploring the secrets of our universe, blending physics and information theory in ways we are only beginning to comprehend. Retrocausality is a fascinating idea in quantum physics, suggesting that events in the future can influence those in the past. To understand this, we must first grasp the unusual nature of quantum mechanics, where particles can exist in multiple states at once, only taking on a definite role when they are observed. This strange behavior challenges our traditional view of time, where past events lead to predictable future outcomes. In some interpretations of quantum physics, particularly those related to entangled particles, there seems to be a connection that transcends the time order we are familiar with. For instance, when two particles are entangled, a measurement made on one particle instantly determines the state of the other, no matter how far apart they are. This puzzling phenomenon raises questions. Could something from the future influence the measurement of a particle, thus affecting the earlier state? While experimental results have hinted at complications in the simple cause and effect structure of time, retrocausality remains largely theoretical. Current scientific consensus doesn't widely accept it, as our understanding of causality is grounded on the flow of time moving from the past to the future. Most physicists prefer to view time in a linear fashion, where effects follow causes, yet concepts in quantum mechanics encourage exciting discussions about the nature of reality and the role of time. While retrocausality intrigues researchers and stirs rich debate, its actual application and confirmation in the realm of quantum physics remain to be seen. The idea invites us to rethink our fundamental assumptions about time and how the universe operates at its deepest levels, making it a captivating subject for both scientists and enthusiasts alike. Hidden variable theories propose that the randomness observed in quantum mechanics might not be fundamental, but rather a result of underlying factors yet to be discovered. Mainstream quantum mechanics describes the behavior of particles as inherently probabilistic, meaning we can only predict the likelihood of finding a particle in a particular state, not the exact state itself until a measurement is made. This acceptance of randomness poses a challenge for those who seek to understand the universe as deterministic, where every event is influenced by prior conditions. Imagine a game of dice. In standard quantum mechanics, the outcome of rolling the dice is unpredictable, reflecting a fundamental uncertainty in nature. However, proponents of hidden variable theories argue there might be hidden parameters or underlying factors that influence those dice rolls, even if we cannot observe or measure them directly. These hidden variables would determine the outcome, suggesting there is a deeper order beyond our current understanding. One of the notable challenges hidden variable theories pose is illustrated through experiments involving entangled particles. When two entangled particles are measured, the results appear correlated in ways that quantum mechanics predicts, defying classical intuition. Hidden variables would need to account for these correlations without introducing instant changes across vast distances, a concept known as locality. This creates debates in the scientific community. Notably, tests inspired by physicist John Bell show that if hidden variables exist, they must satisfy certain conditions. Experimental results have consistently supported quantum mechanics, hinting that if hidden variables do exist, they might not align with our traditional notions of causality and locality. Hidden variable theories challenge the very essence of quantum mechanics by attempting to reintroduce a deterministic framework to phenomena that appear fundamentally random. It represents a significant philosophical divide in understanding the true nature of reality, prompting continued exploration and experimentation in the quest to unravel these mysteries. The idea of a quantum theory of consciousness is an exciting frontier in both science and philosophy. It suggests that the complex workings of our mind might be linked to the strange behaviors observed in quantum physics. To understand this, we first need to consider what quantum physics entails. In simple terms, Quantum physics deals with the tiniest particles that make up everything around us. These particles can behave in ways that seem bizarre, like existing in multiple states at once or being connected instantaneously over vast distances. Some scientists propose that consciousness, the awareness of our thoughts and environment, could arise from interactions at this quantum level. The theory suggests that our brain's neural activity might engage with quantum phenomena to create the rich tapestry of experiences we define as consciousness. Imagine each thought like a cascading ripple, where the underlying fabric is woven from the behaviors of quantum particles. If this connection could be established, it would revolutionize our understanding of both consciousness and the universe itself. However, developing a solid quantum theory of consciousness poses significant challenges. The human brain is vastly complex, and isolating specific quantum effects in brain function remains a daunting task. Current neuroscience provides valuable insights into how the brain processes information, but integrating this with quantum mechanics requires new perspectives and potentially groundbreaking discoveries. While the journey toward a quantum theory of consciousness holds promise, it remains mostly theoretical at this stage. As researchers continue to explore the parallels between quantum mechanics and the workings of the mind, they invite us to ponder profound questions about the nature of reality and our place within it. This ongoing investigation could ultimately lead to a deeper understanding of consciousness, perhaps revealing it as more than just a product of biological processes. Moore's law has traditionally predicted that the number of transistors on a computer chip would double approximately every 2 years, leading to constant increases in computing power. However, as the physical limits of silicon-based technology approach, this law faces significant challenges, and this is where quantum computing steps in. Quantum computers operate on principles of quantum mechanics, which involve the behaviors of particles at the smallest scales. Instead of the traditional bits that represent either 0 or 1, quantum bits or qubits can exist in multiple states at once, thanks to a phenomenon known as superposition. This capability allows quantum computers to perform many calculations simultaneously. Imagine a library filled with countless books. A classical computer would look through each book one by one to find specific information, while a quantum computer could open all the books simultaneously, drastically speeding up the process. This ability to solve complex problems much quicker than classical computers could potentially overcome the slowdowns predicted by Moore's law. Moreover, quantum entanglement allows qubits that are entangled to be correlated with each other despite large distances. This means that changing the state of one qubit instantly influences its entangled partner, enhancing the processing power and ushering in a new era of computation that could tackle problems currently considered unsolvable by classical means. As quantum computing evolves, it shifts the focus from merely increasing the number of transistors to leveraging these advanced principles of quantum mechanics. It proposes a fundamentally different approach to computing, one that could redefine the very frameworks of processing power and problem-solving beyond the limitations of traditional silicon technology. Thus, while Moore's law has been a guiding principle for decades, quantum computing presents an exciting paradigm shift that challenges and potentially transcends it. Quantum computing is a fascinating field, but many misconceptions surround it. One of the most common misunderstandings is that quantum computers are simply faster versions of classical computers. While it's true that quantum computers have the potential to solve certain problems much more efficiently, they are not universally faster for all tasks. Think of it like this. A classical computer is like a skilled chef who can prepare a variety of dishes efficiently, while a quantum computer is like a chef who has a special technique that allows him to create certain complex dishes in a fraction of the time. However, for simpler recipes, the classical chef may still be faster. Another misconception is that quantum computing will replace classical computers entirely. In reality, classical computers will continue to play a vital role in everyday tasks. Quantum computers excel in specific areas, such as factoring large numbers and simulating quantum systems, where they can offer significant advantages. However, for routine tasks like web browsing or document editing, classical computers are likely to remain the go-to option. Many people also believe that quantum computing is an already fully developed technology. The truth is that this field is still in its early stages, with scientists working diligently to overcome various technical challenges. Building a stable quantum computer is remarkably complex due to the delicate nature of quantum bits, or qubits. Unlike traditional bits that can simply be ones or zeros, qubits can exist in multiple states simultaneously, making them both powerful and difficult to manage. Additionally, there's a widespread notion that quantum computers can crack any encryption scheme. While they have the potential to break certain cryptographic methods, particularly those based on large numbers, not all encryption is vulnerable to quantum techniques. Researchers are actively developing new cryptography methods that would be secure even against quantum attacks. Understanding these nuances helps clarify what quantum computing truly is and what it can achieve. Its promise lies not in replacing existing technology, but in offering new capabilities that could transform specific fields, pushing the boundaries of our computational understanding. Quantum computing holds the potential to revolutionize machine learning and artificial intelligence in significant ways. To understand how, let's first consider the nature of classical computers. They process information using bits, which can either be in a state of 0 or 1. In contrast, quantum computers use qubits, which can exist in multiple states simultaneously thanks to a property called superposition. This allows quantum computers to handle vast amounts of information at once. When it comes to machine learning, many algorithms involve searching through massive datasets to find patterns or make predictions. Quantum computers can potentially speed up this process enormously. For example, they can perform certain calculations significantly faster than classical computers by exploring many possible solutions at the same time. This increased speed can lead to quicker training of models, enabling them to learn from data more efficiently. Another exciting aspect is quantum entanglement, which allows qubits that are entangled to be correlated with each other, regardless of the distance separating them. This property can lead to more sophisticated interactions within algorithms, making it possible to analyze complex relationships in data that classical systems might struggle with. Furthermore, some machine learning tasks like optimization problems can be significantly enhanced with quantum techniques. Quantum computers might excel in finding optimal solutions from a vast landscape of options much faster than their classical counterparts. This could open the door to more accurate models in areas like natural language processing, image recognition, and other applications where traditional methods can be limited by computational resources. While quantum computing is still in its early stages, researchers are optimistic about its ability to advance machine learning and artificial intelligence. As the technology develops, we may witness breakthroughs that could reshape entire fields, making machines not only smarter, but also more adaptable in understanding complex data. The journey to harness the full capabilities of quantum computing in AI will undoubtedly bring exciting advancements in the coming years. A quantum neural network is an innovative concept that combines principles of quantum mechanics with artificial intelligence. To understand it, let's start with a basic idea of what a neural network is. Traditional neural networks are systems designed to recognize patterns and make decisions based on data. They mimic the way human brains process information using layers of interconnected nodes. Now, when we bring quantum mechanics into the picture, things get much more intriguing. Quantum mechanics operates on rules that are very different from our everyday experiences. It deals with the smallest particles in the universe, like atoms and photons, where behaviors can seem strange. For example, particles can exist in multiple states at once or be instantaneously connected over vast distances, a phenomenon known as entanglement. In a quantum neural network, each node acts like a quantum bit or qubit. Unlike a traditional bit that can be either a 0 or a 1, a qubit can represent both values at the same time due to a property called superposition. This allows a quantum neural network to process vastly more information simultaneously compared to classical networks. Imagine trying to search for a specific book in a library. A traditional approach would require going through each shelf one by one. However, with a quantum neural network, it's as if you can examine every bookshelf all at once. When it comes to training these networks, quantum algorithms could potentially speed up the learning process, allowing the network to identify patterns much faster than conventional methods. For instance, this might enable it to analyze complex data such as images, sounds, or financial trends with remarkable efficiency. Despite its promise, quantum neural networks are still in the experimental phase. Scientists are working to address many challenges, including the stability of qubits and scaling the technology. However, the potential applications are vast, from improving machine learning tasks to creating more efficient data processing methods. As research continues, quantum neural networks could lead to breakthroughs that we can hardly imagine today, opening new frontiers in both technology and science. Quantum computers are fascinating machines that operate on principles very different from traditional computers. Imagine a traditional computer as a super-fast calculator, processing information in a linear fashion, one step at a time. In contrast, a quantum computer uses the principles of quantum mechanics, allowing it to explore many possibilities simultaneously. This unique ability gives quantum computers a tremendous potential for problem-solving in fields like cryptography, medicine, and materials science. However, the complexity that gives quantum computers their power also makes them challenging to understand and use. Currently, they require a deep knowledge of quantum mechanics and specialized programming languages. This creates a barrier for those who are not trained in science or technology. Despite these challenges, many researchers and companies are working hard to change this landscape. The goal is to simplify the interaction with quantum computers, much like how we interact with traditional computers today. Just as operating systems and user interfaces evolved over decades, quantum computing might follow a similar path toward user-friendliness. With advancements in software that can abstract the complexities of quantum mechanics, it is possible that one day, understanding the basic functionalities and applications of quantum computers could be within reach for non-scientists. As researchers create more intuitive platforms and tools, the hope is that regular users can harness quantum computing power for practical purposes, much like how smartphones have made powerful computing accessible to everyone. The journey to achieve this is ongoing, and while we may not be there yet, the prospects are promising. In time, with continued innovation and education, quantum computers may indeed become user-friendly devices that anyone can utilize. Transistors are the building blocks of modern electronics, and they come in two main types: classical and quantum. Classical transistors, which we have been using for decades, rely on the behavior of electric currents to control the flow of electricity. They function like tiny switches that can either be open, allowing current to pass, or closed, stopping the flow. In this traditional setup, the transistors operate using definite states of electrical charge. On the other hand, quantum transistors harness the principles of quantum mechanics, which is the branch of physics that describes how very small particles behave. Instead of operating with clear yes or no states, quantum transistors can exist in multiple states at once due to a phenomenon called superposition. This means they can represent more information than classical transistors because they can handle multiple possibilities simultaneously, like being both on and off at the same time. Another key difference is entanglement. In quantum systems, particles can become entangled, meaning the state of one particle is directly related to the state of another, no matter how far apart they are. This allows quantum transistors to work in coordination in ways that classical transistors cannot. The result is a potential for much faster processing speeds and more efficient data handling. In practical terms, while classical transistors have already transformed our technology, quantum transistors could open doors to advancements like complicated calculations that are quickly solved, enhanced artificial intelligence, and secure communication systems. Their ability to operate on principles of quantum physics makes them a promising frontier in the quest for more powerful and efficient computing. To understand the difference between analog and digital quantum computers, it helps to first grasp the concept of quantum computing itself. At their core, quantum computers use the principles of quantum mechanics to process information in ways that traditional computers cannot. Analog quantum computers, similar to their classical analog counterparts, process information in a continuous manner. They work by manipulating quantum states along a pathway that resembles a wave. Think of it as adjusting the dials on a complex radio. Instead of flipping switches to create distinct and separate signals, you are continuously tuning the frequency to get the clearest reception. This type of quantum computer is well suited for specific tasks, like simulating certain physical systems or solving complex optimization problems, where the solution can exist in a range of possibilities rather than discrete options. On the other hand, digital quantum computers operate more like the classical computers we're familiar with. They use distinct quantum states to represent bits of information, but these bits take the form of qubits. Each qubit can exist in multiple states simultaneously, thanks to a property called superposition. When working with digital quantum computers, think of each qubit as a switch that can be either on or off, or both at the same time, allowing for more complex calculations. This setup allows them to perform a wide range of algorithms that can tackle problems such as cryptography and factoring large numbers efficiently. While analog quantum computers focus on continuous variations similar to analog signals, digital quantum computers utilize discrete states like digital signals to perform calculations. Each type has its strengths, catering to different kinds of problems in the expansive landscape of quantum computing. The idea of quantum computing creating true artificial intelligence sparks a fascinating dialogue about the future of technology. At its core, quantum computing harnesses the bizarre principles of quantum mechanics, allowing it to process information in a way that classical computers cannot. It's as if traditional computers operate like single-lane roads, while quantum computers can navigate multiple routes simultaneously, opening up a vast realm of possibilities. To understand how this might relate to artificial intelligence, consider that both fields deal with complex computations and large amounts of data. Quantum computing could potentially expedite tasks that require immense processing power, such as analyzing patterns in enormous datasets or simulating complex systems. This speed and efficiency could significantly enhance the capabilities of AI, allowing it to learn from and adapt to data more rapidly and in more intricate ways than ever before. However, achieving true artificial intelligence, machines that can think and learn autonomously like a human, is about more than just computational power. It requires nuanced understanding, creativity, and the ability to understand context. While quantum computing can amplify the cognitive abilities of AI systems, it does not automatically grant them the higher-level consciousness or creativity that characterize human thought. Moreover, the journey toward achieving true artificial intelligence includes ethical considerations and the understanding of consciousness itself. The advances brought about by quantum computing could indeed push the boundaries of what we consider possible with AI, but whether this leads to a consciousness akin to our own remains a question filled with both promise and uncertainty. It suggests that while quantum computing may catalyze advancements in AI, the path to true intelligence is complex and involves much more than just powerful computations. The uncertainty principle is a fundamental concept in quantum mechanics that states you cannot precisely know both the position and momentum of a particle at the same time. This means that the more accurately you measure one, the less accurately you can measure the other. This principle affects quantum computing significantly because the nature of quantum bits or qubits is deeply rooted in these principles. In classical computing, information is stored in bits, which are either 0 or 1. However, qubits can exist in a state of both 0 and 1 simultaneously, thanks to a phenomenon called superposition. This unique ability allows quantum computers to process vast amounts of information at once. However, the uncertainty principle introduces a layer of complexity. When we try to measure a qubit's state, the act of measurement itself disturbs the qubit, altering its state in a way that is unpredictable. Consequently, while superposition and entanglement, the linking of qubits, allow for powerful calculations and secure communication, they are inherently affected by the uncertainties associated with quantum mechanics. Engineers and scientists must account for these effects when designing quantum computers. They use error correction techniques and maintain the delicate balance required to manipulate qubits without disturbing them too much. Ultimately, the uncertainty principle is a central feature of the quantum world. It not only challenges our concepts of computation, but also opens up new possibilities. By embracing the unpredictable nature of quantum systems, researchers are pushing the boundaries of technology, potentially leading to advancements in fields such as cryptography and material science. Thus, the uncertainty principle, while introducing challenges, also drives innovation in quantum computing. Quantum randomness is a fascinating concept that plays a crucial role in modern secure encryption methods. In traditional encryption systems, keys generated through algorithms can sometimes be predictable, like a recipe that could potentially be figured out with enough time and resources. This predictability exposes these keys to various forms of attacks, where a hacker can guess or compute them, compromising the security of sensitive information. In contrast, quantum randomness arises from the fundamental unpredictability of quantum mechanics. Imagine trying to predict the outcome of a coin toss where the coin is spinning in such a way that we have no idea where it will land. In the quantum world, this level of uncertainty is inherent in the very nature of particles. When we measure a quantum state, the outcome is truly random, not just seemingly random. This unique property is harnessed to create encryption keys that are completely unpredictable and unique for each usage. For instance, quantum key distribution uses pairs of particles like photons in special states. When these particles are sent from one party to another, any attempt by an eavesdropper to intercept them changes the state of the particles, immediately alerting the communicating parties to the presence of an intruder. Because these keys are generated based on quantum phenomena, they can theoretically be proven to be secure, relying fundamentally on the laws of physics rather than on mathematical complexity. This method ensures that even if someone could intercept the key, they would not be able to recreate it. Thus, quantum randomness provides a level of security that is not just technological, but deeply rooted in the principles of nature itself, paving the way for a much safer digital future. Quantum technology has the potential to enhance our ability to detect alien life by improving the sensitivity and precision of our instruments. Imagine trying to hear a whisper in a crowded room. That's somewhat like the challenge we face when looking for signals from distant civilizations or tiny life forms on other planets. Standard technology can miss these faint signals, but quantum advancements can amplify them, allowing us to sift through noise more effectively. One exciting area of application is quantum sensors. These devices can measure incredibly small changes in magnetic fields, temperatures, or light, enabling scientists to pick up subtle signs of life or technology. Think of these sensors as being incredibly fine-tuned, capable of detecting even the slightest fluctuations that might indicate biological or technological activity in space. Additionally, quantum communication could provide a way to send and receive information across vast distances without losing quality. This might open pathways for advanced interstellar messaging, creating a framework for communicating with any intelligent life we may discover. While we have not yet developed these technologies fully to search for alien life directly, the possibilities are awe-inspiring. Quantum technology offers tools that could potentially revolutionize our search for alien life, enhancing our ability to explore the universe and understand the signals it might hold. Quantum mechanics holds the potential to transform space navigation in ways that traditional methods cannot. At its core, quantum mechanics deals with the behavior of extremely small particles, and it introduces concepts that defy common sense to some degree. For space navigation, one of the most fascinating applications of quantum mechanics is through the use of quantum sensors. Imagine a navigation system that can measure changes in its environment with astounding precision. Quantum sensors work by capitalizing on the strange properties of particles at the quantum level. For instance, they can detect minute variations in gravitational fields, which could help identify the presence of celestial bodies or anomalies in space that affect a spacecraft's trajectory. This precision could enable spacecraft to navigate more accurately than with current methods. Another exciting prospect lies in quantum entanglement, a phenomenon where two particles become connected in such a way that the state of one instantly influences the state of the other, regardless of the distance between them. In theory, this could lead to new forms of communication that are instantaneous, making it possible for spacecraft to receive critical information from Earth or other vessels without delay. Such advancements could drastically reduce the time needed for maneuvering spacecraft and making navigational decisions. Moreover, quantum computing may play a significant role in the future of space exploration. Unlike traditional computers that process information sequentially, quantum computers can analyze vast amounts of data simultaneously. This capability could enable complex calculations for navigation and route optimization, factoring in variables like gravitational forces from multiple bodies, space debris, and other challenges that would arise over extended journeys through space. As we continue to discover more about quantum mechanics and engineered systems derived from it, the possibilities for improving space navigation are vast. By leveraging the unique properties of the quantum world, we may pave the way for safer and more efficient journeys across the cosmos, bringing once-imagined interstellar travel a step closer to reality. Quantum entanglement can fundamentally change the way we think about communication across vast distances in space. To understand it, imagine two particles that are connected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This is like having two magic coins. If you flip one and it shows heads, the other, wherever it is in the universe, will also show heads instantly. In the context of deep space communication, entangled particles could potentially allow information to be shared between distant spacecraft or even between Earth and distant missions without the usual delays caused by the speed of light. Current technology relies on sending signals that travel through space, which takes time, especially when distances are enormous, like traveling to another star system. With quantum entanglement, the speed at which the state of one particle affects its partner is instantaneous, meaning that it could, in theory, provide a method of communication that is not limited by traditional speed of light constraints. However, there's a catch. While entanglement can ensure that linked particles remain correlated, it does not allow for the direct transmission of information in a way we can easily use today. Researchers are exploring how to harness this phenomenon, which could lead to breakthroughs in secure communications and faster-than-light signaling concepts. Although we are still in the early stages of understanding and utilizing quantum entanglement for communication, it opens up fascinating possibilities for the future of deep space exploration. Scientists are imagining a time when this quantum link could help connect humanity across light years, transforming how we communicate in the universe. Quantum computing holds the potential to unlock many mysteries of the universe, including the intricate behaviors of black holes. To understand how this works, let's first consider what makes black holes so fascinating and complex. Black holes are regions in space where gravity is so strong that nothing can escape from them, not even light. This means they can warp the very fabric of space and time, an effect that is described by the laws of physics, particularly general relativity. Simulating black holes using traditional computers is challenging. Standard computers process information in a linear manner, meaning they handle one task at a time, which can limit their ability to model the vast and tangled equations needed to describe black hole phenomena accurately. In contrast, quantum computers operate on the principles of quantum mechanics, which allows them to process multiple possibilities at once. This unique capability means they could run simulations that capture the complexity of a black hole more efficiently. Imagine trying to model a black hole's formation, its event horizon, and how it interacts with nearby matter. A quantum computer could explore many different scenarios simultaneously, looking at various factors like rotation, mass, and the surrounding environment. This ability could lead to better insights into how black holes evolve and behave, potentially revealing new aspects of their connection to the fundamental laws of physics. Moreover, these advanced computers could help scientists test theories that combine quantum mechanics and gravity, fields that are notoriously difficult to unify. By running sophisticated simulations, researchers could gain insights that improve our understanding of everything from the creation of black holes to their effects on space-time. While there is still much work to be done, quantum computing presents a promising avenue for simulating the intricate behaviors of black holes. This could not only enhance our understanding of these cosmic giants, but also advance the broader field of theoretical physics. Quantum physics plays a subtle but fundamental role in our quest to find habitable planets. At its core, quantum physics examines the behavior of tiny particles, which can be quite different from what we observe in our everyday lives. One crucial aspect of quantum physics is the concept of superposition, where particles can exist in multiple states at once until they are observed. This principle aids scientists in understanding molecular interactions that contribute to conditions for life. When astronomers explore distant stars to find planets, they utilize a technique called spectroscopy. This involves analyzing the light that passes through a planet's atmosphere. Here, quantum mechanics is at work. Light interacts with molecules in such a way that it provides telltale signs of specific elements and compounds present. By identifying gases like oxygen or methane, which are often associated with biological processes, scientists can infer the potential for life. Moreover, another quantum phenomenon, entanglement, showcases how particles can become linked in ways that seem to defy distance. While entanglement is more abstract in its application to exoplanet research, it influences how we understand information transfer, including signals sent from distant stars. This helps refine our methods to analyze signals, leading to better detection of Earth-like characteristics on faraway worlds. In addition, quantum physics underpins our understanding of material properties. Elements and compounds necessary for life, such as water, are governed by the principles of quantum mechanics. By studying how these substances behave under various conditions, scientists can determine the likelihood of similar environments elsewhere in the universe. Ultimately, while the relationship may not be immediately apparent, quantum physics provides the principles that enhance our exploration methods, guiding us in identifying and analyzing planets where life could potentially thrive. This intricate web of knowledge leads to deeper insights into our universe and the places much like our home that might exist among the stars. Building a quantum computer in space presents several exciting challenges. First and foremost, quantum computers rely on delicate quantum bits, or qubits, which are incredibly sensitive to their environment. In space, this environment is filled with radiation, temperature fluctuations, and vibrations from equipment and spacecraft systems. These factors could easily disrupt the delicate states of the qubits, leading to errors in computations. Another challenge is the need for precise control over qubits. On Earth, this is often achieved through complex cooling systems and vacuum environments to minimize interference. In space, maintaining controlled temperatures and isolating qubits from external disturbances proves difficult. Engineers would need to develop new ways to ensure that qubits remain stable and controllable, even in the unpredictable conditions of space. Communication is also a significant concern. Quantum entanglement, a key feature that allows qubits to be interconnected, can be affected by distance and obstacles. In space, signaling across vast distances or through physical barriers can introduce delays and potential loss of data. Creating a reliable communication system that preserves the integrity of quantum information while transmitting it over great distances is vital. Power supply is another hurdle. Quantum computers typically require significant amounts of energy for operation and cooling. In a space environment where resources may be limited, developing efficient power sources that can sustain the demands of a quantum system is crucial. Lastly, collaboration between multiple scientific disciplines is essential. The fusion of quantum mechanics, engineering, and aerospace technology requires inputs from various experts, all of whom need to ensure their designs work harmoniously. This collaborative effort must continue over the long duration of space missions, which can pose logistical challenges. While the potential of space-based quantum computing is vast, overcoming issues related to environmental sensitivity, control, communication, power supply, and interdisciplinary collaboration will be key to making these advanced systems a reality in orbit. Gravitational waves are tiny ripples in spacetime caused by massive cosmic events, like merging black holes or supernova explosions. Detecting these waves is incredibly challenging because they shift distances by amounts so small they are nearly impossible to measure. Traditional methods of detection, like those used in large observatories, rely on lasers and mirrors, but quantum sensors can potentially enhance this process significantly. Quantum sensors leverage the principles of quantum mechanics, which govern the behavior of very small particles. One key advantage is their ability to measure changes in position with extreme sensitivity. By using particles called photons, quantum sensors can pick up on the minute changes caused by passing gravitational waves. Think of it like using a finely tuned instrument to hear the faintest sound. Quantum sensors can hear these tiny disturbances in space-time much better than standard techniques. Moreover, these sensors can exploit a phenomenon known as quantum entanglement, where particles become linked and share information instantaneously. This enables them to gather data in ways that classical sensors cannot, potentially allowing for a clearer picture of the gravitational waves as they pass through Earth. While traditional gravitational wave detectors have made remarkable progress, quantum sensors represent a new frontier. They promise to improve detection accuracy, helping scientists to observe and understand some of the most profound events in the universe. quantum physics might hold the keys to unlocking the concept of faster-than-light travel. At the heart of this exploration is the idea of quantum entanglement, a strange phenomenon where particles become linked so that the state of one instantly influences the state of another, no matter the distance separating them. Imagine two entangled particles as dance partners, perfectly synchronized regardless of how far apart they are. This instant connection suggests that information can be shared almost instantaneously, hinting at possibilities beyond our usual understanding of space and time. Building on this idea, theoretical physicists have proposed concepts such as warp drives and wormholes. A warp drive would function similarly to stretching and bending space itself. Instead of moving an object through space at high speeds, it would contract the space in front of it and expand the space behind it. This would create a sort of bubble where the laws of physics, as we usually understand them, could be altered, allowing for effective, faster-than-light travel without breaking the fundamental rules set by relativity. Wormholes add another layer to this vision. By theorizing the existence of shortcuts in space-time, we could connect two very distant points through a tunnel-like structure. While traversing a wormhole could theoretically allow for near-instantaneous travel across vast distances, navigating through one involves numerous complexities and uncertainties. However, these concepts remain firmly in the realm of speculation. Quantum mechanics introduces deep uncertainties and behaviors that challenge traditional physics, and making practical use of these phenomena would require breakthroughs that we have not yet achieved. As scientists study these ideas further, the dream of moving faster than light sparks imagination, showcasing the dizzying possibilities of the universe we are still learning about. The idea of a quantum spacecraft captures the imagination and points towards an intriguing frontier in space travel. To understand this concept, we first need to grasp what quantum technology is. At the quantum level, particles behave in ways that seem strange compared to our everyday experiences. They can exist in multiple states at once, a property called superposition, and they can be interconnected even across vast distances through a phenomenon known as entanglement. If we imagine a spacecraft harnessing these quantum principles, we could potentially explore new methods of propulsion and navigation. For instance, quantum technology might allow for incredibly precise measurements of gravitational fields, which would enhance our understanding of where we are in space. This improved accuracy could make navigation through the cosmos far more efficient. Moreover, there's a concept of quantum communications. In a future where such a spacecraft exists, it might be able to communicate instantly with Earth or other spacecraft, even if they are light years apart. This could revolutionize how we share information and coordinate missions across the vastness of space. However, building a quantum spacecraft faces significant challenges. The technology is still in its infancy, and creating stable quantum states that can function in the harsh environment of space is a monumental task. Engineers would have to overcome difficulties related to maintaining those quantum states against interference from the surrounding space environment. Though the vision of a quantum spacecraft sounds promising and full of potential, it remains speculative. The groundwork has begun, and advancements in quantum technology may one day lead us to explore these exciting possibilities. As research continues and our understanding grows, the dream of such a spacecraft might eventually take flight. In the vast emptiness of space, quantum systems experience intriguing behaviors shaped by the vacuum around them. Unlike the vacuum we might think of in daily life, which seems entirely empty, the quantum vacuum is filled with fluctuating energy fields. These fields give rise to particles that fleetingly appear and then vanish due to the principles of quantum mechanics. In this environment, particles are constantly popping in and out of existence. This phenomenon is known as vacuum fluctuations. These tiny, temporary particles can influence the properties of quantum systems nearby, leading to effects like the Casimir effect, where two closely spaced objects can experience a force due to changes in vacuum energy between them. Furthermore, when you consider particles like electrons or atoms, their properties do not change just because they find themselves in a vacuum. Instead, they exist as wave functions, representing the probabilities of finding them in various states or locations. The absence of interference from other particles allows these quantum entities to exhibit their fundamental behaviors more clearly, unmasked by external influences. This interaction with the vacuum can lead to exciting processes, such as the creation of exotic particles in high-energy environments like those found near black holes or during cosmic events. Overall, the vacuum in space is anything but empty. It is a bustling realm where quantum systems interact in profound and often surprising ways. Quantum biology is a fascinating area of study that blends principles from quantum mechanics with biological processes. To understand this field, imagine biology as a complex machine made up of countless tiny components. At the heart of this emerging field is the realization that some of these biological processes might actually operate according to the unusual rules that govern the quantum world, where particles can exist in multiple states at once and can instantaneously affect one another over large distances. One of the key reasons quantum biology is gaining attention is due to its potential to explain certain biological phenomena that seem difficult to grasp through traditional biology alone. For example, consider photosynthesis, the process by which plants convert sunlight into energy. Researchers have found that plants might use quantum mechanics to transfer energy more efficiently, allowing them to capture light and convert it into chemical energy in a way that seems almost miraculous. Similarly, the phenomenon of bird navigation sheds light on quantum biology's implications. Some species of birds appear to be able to sense the Earth's magnetic field using proteins in their eyes that are thought to operate with quantum effects. This allows them to navigate vast distances with remarkable accuracy, and understanding how this works could revolutionize our knowledge of both biology and physics. As scientists explore these intriguing connections, they are uncovering that the microscopic world of atoms and particles may play a critical role in processes we observe in living beings. The blending of these two disciplines opens doors to new technologies, medical advancements, and deeper insights into life itself. Consequently, quantum biology is not just an academic curiosity. It's a rapidly growing field that could reshape our understanding of the natural world. Quantum tunneling is a fascinating phenomenon that can play a crucial role in enzyme reactions. Imagine that in a chemical reaction, certain particles like protons or electrons need to overcome an energy barrier to move from one place to another. In classical terms, if a particle doesn't have enough energy, it simply cannot cross this barrier, similar to how a ball needs to have enough strength to roll over a hill. However, in the strange world of quantum mechanics, particles behave differently. They don't follow the same rules as larger objects. Instead, they can exist in many states at once, a concept known as superposition. This means that even if a particle lacks the energy to climb over a barrier, it has a chance of tunneling through it as if the barrier didn't exist. Picture a ghost walking through a solid wall. Quantum tunneling allows particles to bypass barriers without needing to climb over. In the context of enzymes, which are biological catalysts speeding up reactions, this tunneling can facilitate reactions that would otherwise be slow or improbable. When enzymes bind to their substrates, they create a unique environment that can alter the probabilities of different outcomes. The enzyme might position these particles in a way that enhances their likelihood of tunneling through energy barriers, thus speeding up the reaction process. So during an enzyme reaction, while we typically think in terms of energy requirements to push particles over barriers, quantum tunneling introduces a probability that allows for surprisingly efficient reactions. This blending of biology and quantum physics underscores how enzymes are not just simple tools. They're intricately connected to the bizarre rules of the quantum world. Ultimately, this connection shines a light on the complexity of life at its most fundamental levels. Birds possess an extraordinary ability to navigate using Earth's magnetic field, and quantum physics plays a fascinating role in this process. At the heart of this navigation is a special protein found in the bird's eyes, which contains molecules sensitive to magnetic fields. These molecules respond to light, and when they absorb photons, particles of light, they undergo a change that directly relates to magnetic fields. Imagine a small compass needle, which aligns with Earth's magnetic pull. In birds, this alignment is influenced at the quantum level. Electrons, which are tiny charged particles, can exist in multiple states simultaneously, a concept known as superposition. By existing in this state, they can react to the slightest changes in the magnetic field around them. When a bird sees light, these molecules change slightly, sending signals to the bird's brain that helps it to sense direction. This process allows birds to visually interpret the magnetic field, almost as if they have a built-in compass in their vision. The quantum effects tied to these molecules serve as a biological GPS system, guiding them on their migratory journeys across vast distances. Scientists are still unraveling the exact mechanisms, but it's clear that the principles of quantum physics help illuminate how these remarkable creatures utilize invisible forces to find their way. The incredible intersection of biology and physics showcases nature's ingenuity and our continuing quest to understand the universe's complexities. The idea that human consciousness might be connected to quantum phenomena is a captivating topic that blends neuroscience and quantum physics. At its core, consciousness is our awareness and understanding of ourselves and our surroundings. Scientists study consciousness mainly through the brain's biological and chemical activities. However, some theories suggest that the brain may operate at a level where quantum effects could play a role. Quantum mechanics deals with the behavior of very tiny particles, like atoms and their components. It's a strange world, where particles can be in multiple states at once and can influence each other no matter how far apart they are. Some researchers propose that processes happening in the brain at the molecular level might exhibit similar strange behaviors. This could contribute to our thoughts, perceptions, and the overall experience of being conscious. One theory, for instance, posits that certain structures in the brain's cells, called microtubules, could harness quantum mechanics to facilitate consciousness. If these particles behave in ways that are not fully understood, it might explain some of the more elusive aspects of our conscious experience. Nonetheless, it is essential to note that these ideas are highly speculative and not widely accepted among scientists. While the thought of consciousness being a quantum phenomenon is intriguing, the scientific community has not reached a consensus. Understanding consciousness remains one of the biggest mysteries in science, and exploring possible quantum connections could open up new avenues of research, but more evidence is needed to support such theories. Photosynthesis is the process by which plants, algae, and some bacteria convert sunlight into energy. This process captures energy from sunlight and uses it to create food, specifically in the form of glucose. But how is this incredible transformation linked to the principles of quantum mechanics, particularly quantum coherence? At the heart of photosynthesis are structures known as chlorophyll molecules. These molecules absorb light energy and initiate a complex series of reactions. Interestingly, when light hits a chlorophyll molecule, it doesn't just get absorbed in a straightforward manner. Instead, the energy can spread out across multiple chlorophyll molecules, much like ripples in a pond. This spreading of energy happens because of a phenomenon called quantum coherence, where particles exist in a state that can link their behavior even over distances. In this state, the energy from sunlight can be transported efficiently to a reaction center, where it is ultimately converted into chemical energy. The ability for this energy to flow smoothly is thought to be enhanced by coherence, which allows it to make use of all possible paths to reach the reaction center, rather than taking a single, less efficient route. Researchers suggest that this quantum coherence might last longer than scientists initially expected, indicating that living organisms can utilize quantum effects to improve the efficiency of photosynthesis. This interplay not only showcases the beauty of nature's design, but also opens the door for potential new technologies inspired by how plants harness energy so effectively. Understanding this connection could lead to innovations in energy capture and storage, mimicking nature's own processes. Quantum entanglement is a fascinating concept from the realm of physics that describes a unique connection between particles. Imagine two entangled particles as two dancers that move in perfect harmony, regardless of the distance between them. When one dancer makes a move, the other responds instantly, even if they are light years apart. This phenomenon challenges our understanding of how things connect in the universe. When it comes to human thought processes, the link to quantum entanglement is not straightforward. Our thoughts and brain activity are generally understood through the lens of classical neuroscience, which involves chemical and electrical signals in the brain rather than quantum mechanics. The idea that quantum entanglement could influence human cognition suggests that there might be deeper yet still unexplored interactions happening at a fundamental level. Some scientists have proposed that quantum effects might play a role in consciousness or cognitive functions, suggesting that our brains could potentially utilize quantum properties in processing information. This perspective remains speculative and is the subject of much debate within the scientific community. While there is enthusiasm about the interplay between quantum mechanics and biological systems, current research has not definitively shown how entanglement might directly impact how we think or make decisions. Understanding human thought is a complex blend of many factors, including biology, psychology, and possibly even elements we have yet to fully discover. While quantum entanglement is a remarkable phenomenon of nature, its direct impact on human thought processes remains a tantalizing possibility rather than an established fact. Scientists continue to explore this exciting area, hoping to uncover new insights that may one day bridge the gap between quantum physics and our understanding of consciousness. Quantum physics plays a surprisingly significant role in the biological processes that can lead to DNA mutations. At its core, quantum physics explains the behavior of very tiny particles, such as electrons and protons, which make up atoms. These atoms form the building blocks of DNA. In the world of quantum mechanics, particles do not always follow predictable paths. They can exist in multiple states at once, a phenomenon known as superposition. This means, at a very small scale, that there is a level of uncertainty and possibility for every particle's location and state. When particles interact, like when radiation or chemicals hit DNA, their behavior can lead to unexpected changes. One fascinating aspect is quantum tunneling, where particles can pass through energy barriers that would normally be insurmountable if we only consider classical physics. In the context of DNA, this could mean that electrons might jump from one atom to another within the DNA structure in a way that causes a rearrangement or damage, leading to mutations. Additionally, our understanding of genetics includes recognizing that mistakes in DNA copying can happen. These errors are often corrected by sophisticated cellular machinery. However, if quantum effects create instability, it could impede these correction processes, leading to mutations being preserved rather than fixed. So, while mutations can typically be caused by environmental factors or copying errors, quantum physics introduces a layer of complexity. It suggests that on a microscopic level, even the fundamental particles can behave in ways that impact genetic stability and mutation rates, illustrating how the smallest elements of the universe can have significant consequences on our biological framework. Near-death experiences often provoke deep curiosity, raising questions about consciousness and existence itself. Some researchers speculate that quantum mechanics could offer insights into these phenomena. At its core, quantum mechanics describes the behavior of particles at the smallest scales, where strange occurrences challenge our everyday understanding of reality. One intriguing aspect of quantum mechanics is the concept of superposition, which suggests that particles can exist in multiple states or locations at the same time. This idea parallels how near-death experiences can feel surreal or disconnected from physical reality. Some theorists propose that consciousness might also exist in a state of superposition, suggesting that during near-death experiences, individuals could tap into alternate states of consciousness or a heightened awareness beyond our normal sensory perception. Additionally, quantum entanglement presents another fascinating avenue of thought. This phenomenon occurs when particles become connected in such a way that the state of one can instantaneously affect the state of another, regardless of the distance separating them. Some argue this might imply a form of interconnectedness among all consciousness, possibly supporting the feeling of unity or oneness reported by those who have experienced near-death situations. Despite these intriguing ideas, it's essential to note that the connection between quantum mechanics and consciousness remains speculative. Scientifically, these concepts haven't been conclusively proven to explain near-death experiences. Continuing research may broaden our understanding of both quantum physics and the profound mystery of human consciousness, leaving us with more questions than answers about what lies beyond life as we know it. Teleportation of biological matter, while a fascinating concept, remains firmly in the realm of theoretical exploration, largely rooted in the field of quantum physics. To grasp this idea, we can start with the notion of quantum teleportation, which has been demonstrated with particles like photons and atoms. This process involves the transfer of the state of a particle from one place to another without the particle itself moving through the intervening space. Now, when we think about applying this concept to biological matter, we encounter a multitude of challenges. Biological organisms are immensely complex, composed of billions of atoms organized in intricate ways to create living systems. To teleport a living being, we would need to accurately scan and describe every atom in its body, including their positions and connections. This would result in an enormous amount of data and would require technology far beyond our current capabilities. Furthermore, even if we could map out this atomic information perfectly, we face the issue of reassembling those atoms in a different location without introducing errors. Any mistake in the process could lead to dramatic consequences, potentially altering the organism in harmful ways or even rendering it lifeless. Additionally, there's the question of what it means for consciousness and identity. If an exact replica of a person is created somewhere else, is that person still the same individual or just a copy? These philosophical considerations complicate the idea further. While the theory of teleportation advances in the realm of quantum particles, teleporting biological matter involves complexities that are still purely hypothetical and could require breakthroughs in technology and understanding of both physics and biology before becoming anything close to a reality. Quantum biology is an exciting field that examines how the principles of quantum mechanics, which traditionally describe the behavior of tiny particles, may influence biological processes. This challenges long-standing views about how life functions and evolves. Let's start by considering how life has often been understood, primarily through physical and chemical reactions occurring in cells, all according to predictable laws. However, recent studies suggest that quantum effects might play a role in significant biological activities. For instance, consider photosynthesis, the process by which plants convert sunlight into energy. Scientists have discovered that during this process, plants utilize quantum coherence, a state where particles are connected in such a way that they can behave as one coherent entity. This allows them to efficiently transfer energy captured from sunlight to the sites where it is used, much quicker than what pure chemical reactions would typically allow. Another fascinating example is the navigation of birds during migration. Certain species of birds seem to be able to detect Earth's magnetic field, possibly due to a quantum process occurring in a protein in their eyes. This has led to the idea that their ability to sense direction relies on quantum entanglement, an interconnectedness between particles that can lead to instantaneous effects over distance. These examples suggest that life might not just be a series of chemical reactions happening on a macroscopic scale, but could instead be deeply rooted in quantum phenomena. This revelation leads to a re-evaluation of evolutionary processes. If quantum effects can influence how organisms interact with their environment and how they adapt, it might indicate that evolution is not solely based on simple variations and natural selection, but also involves quantum-level interactions that were previously overlooked. Quantum biology presents a more complex picture of life and evolution, suggesting that at the smallest scales, unique and unpredictable factors could drive the development of living systems in ways that challenge our traditional understanding of biology. As researchers delve deeper into this emerging area, they may uncover insights that reshape our comprehension of life itself. Quantum mechanics opens fascinating avenues for understanding the intriguing concept of time travel. At its core, quantum mechanics deals with the behavior of tiny particles, revealing a world where the usual rules of physics often bend. One intriguing aspect is the idea of superposition, where particles can exist in multiple states at once until they are observed. This raises questions about reality itself and whether time, as we know it, is a linear progression or a more complex arrangement of possibilities. Additionally, entanglement is another key feature of quantum mechanics. Imagine two particles that become intertwined in such a way that the state of one instantly affects the state of the other, regardless of the distance separating them. This phenomenon can suggest a kind of interconnectedness across time, as if actions in one moment could influence different moments elsewhere. When we think of time travel in a quantum framework, concepts like parallel universes start to emerge. The many worlds interpretation posits that every action creates branches of reality where different outcomes unfold simultaneously. This raises the tantalizing possibility that traveling through time could mean navigating between these various realities rather than moving through a single, straight timeline. Moreover, some physicists propose theoretical constructs like closed time-like curves, which are paths through space-time that loop back on themselves. In such models, if you could travel around one of these curves, you might return to an earlier point in your own timeline, almost as if stepping into a time machine. While quantum mechanics provides these compelling ideas, it also introduces complex challenges and paradoxes, such as the famous grandfather paradox, where changes to past events might render your own existence impossible. The exploration of time travel remains largely theoretical and speculative, with much still to be understood. Nevertheless, the intersection of quantum mechanics and the nature of time continues to inspire intriguing discussions and research, suggesting that the secret to time travel could be hidden in the quantum realm waiting to be discovered. The rise of quantum computers offers unprecedented capabilities that could transform many fields, including military applications. However, this advanced technology raises significant ethical concerns. With their ability to process information at incredible speeds, quantum computers could crack codes and breach security systems that are currently considered nearly impenetrable. This potential gives military forces a tactical advantage, which may lead to an arms race, as nations scramble to develop their own quantum technologies in an effort to not fall behind. Another concern centers around issues of accessibility. As this technology evolves, it might not be universally available or controlled. The question then becomes, who gets to wield such power? A few nations or corporations could dominate this technology, creating inequalities in global security and power dynamics. This could foster an unstable environment where the balance of power shifts unpredictably, resulting in heightened tensions or conflicts. Moreover, there is the issue of unintended consequences. Military applications of quantum computing could lead to the development of advanced surveillance systems, undermining privacy and civil liberties. Imagine a world where data can be processed and analyzed at speeds that outpace current encryption methods, potentially exposing sensitive information about individuals and organizations. This raises questions about the morality of such surveillance and the potential for misuse. Ethically, we must also consider how quantum technology might change the nature of warfare itself. If robots or autonomous systems rely on quantum computing for real-time decision-making in combat, the implications for accountability are profound. Who would be responsible for the actions of a machine when it operates at speeds no human can match? The fog of war could thicken, making it difficult to determine blame in cases of mistakes or military engagements gone awry. As we progress toward a future with quantum computing, it becomes vital to engage in deep, thoughtful discussions about these ethical implications. We must weigh the advancements against the potential risks to society and ensure that safeguards are in place. By considering these questions now, we can shape a future where technology serves to improve human life rather than significantly complicate it through conflict and inequality. Quantum computing is revolutionizing drug discovery and medicine in astonishing ways. Traditional computers work like very fast calculators, processing information in a linear fashion. In contrast, quantum computers leverage the principles of quantum mechanics to perform complex calculations simultaneously. This unique capability allows them to analyze vast amounts of data much more efficiently than ever before. One of the primary challenges in drug discovery is understanding how molecules interact with each other. Current methods often rely on approximations that can miss critical interactions, which lead to ineffective drugs or unexpected side effects. Quantum computers can simulate molecular structures and interactions at an incredibly detailed level, incorporating all possible behaviors of the particles involved. This means researchers can predict which compounds are most likely to be effective as new drugs much faster and with greater accuracy. Moreover, quantum computing can help identify new drug candidates by searching through countless potential molecules in a fraction of the time it would take traditional methods. Imagine sifting through a library filled with millions of books to find the best one on a specific subject. A quantum computer could instantly browse through all those options, comparing and contrasting information in real time, facilitating the discovery of promising new therapies. In addition to drug discovery, quantum technology holds the potential to enhance personalized medicine. By processing and analyzing complex patient data, quantum computers could help tailor treatments specifically to individuals. This represents a shift towards a more individualized approach to healthcare, where treatments are based on a detailed understanding of a person's unique genetic makeup. Ultimately, The blend of quantum computing's power and the intricacies of drug discovery and medicine could lead to more effective therapies, faster development times, and the possibility of treating diseases that currently have no known cure. As this field progresses, the implications for human health could be profound, offering hope for a healthier future. Quantum technologies have the potential to revolutionize many industries, and some experts believe they could indeed spark a new industrial revolution. At the heart of quantum technologies is the concept of quantum mechanics, which describes the unique behaviors of matter and energy at the smallest scales. While classical technologies operate on predictable outcomes, quantum systems can exist in multiple states at once, allowing for new possibilities in computing, communication, and sensing. One exciting application of quantum computing is its ability to perform calculations at speeds far beyond what classical computers can achieve. Imagine solving complex problems, such as optimizing large systems or simulating molecules for drug discovery in a fraction of the time it currently takes. This could lead to breakthroughs in medicine, materials science, and logistics, effectively transforming how these industries operate. Quantum communication promises to enhance security and data transmission. By leveraging the principles of quantum entanglement, it is possible to create communication networks that are practically immune to eavesdropping. Encrypting data using quantum methods ensures that only the intended recipient can access the information, fostering a new level of privacy and security in our interconnected world. Sensing technologies also stand to benefit significantly. Quantum sensors can detect changes in fields like gravitational forces or magnetic fields with incredible precision. This heightened sensitivity could improve everything from navigational tools to environmental monitoring, providing deeper insights into our world. The blending of quantum technologies with various industries could drastically shift how we approach problems, leading to enhanced efficiencies, security, and capabilities that seemingly belong to science fiction. As researchers continue to develop practical applications, we may well be standing on the brink of a new era of innovation, a transformative chapter in the history of technology and society. The journey toward the widespread use of quantum technology faces several significant hurdles. One of the main challenges is technical complexity. Quantum systems operate on principles that contrast sharply with our everyday experiences. Concepts like superposition and entanglement can be difficult to grasp, both for researchers developing these technologies and for potential users considering their practical applications. Another major barrier is the issue of stability and error rates. Quantum bits, or qubits, are highly sensitive to their environments. They can lose their quantum state easily due to disturbances, which makes reliable, error-free operations difficult. Scientists are working hard to create qubits that can maintain their state longer, but achieving this remains a complex task. Just imagine trying to balance a delicate spinning top. Even a slight touch can topple it. The cost of developing and maintaining quantum technology also poses a challenge. Building the infrastructure necessary for quantum computing, like sophisticated cooling systems and advanced cryogenic equipment, requires significant financial investments. This can limit the number of companies and institutions that are able to venture into quantum research and innovation. Furthermore, the existing technological ecosystem presents a hurdle. Many industries are built around classical computing methods. Integrating quantum technology into these systems would require not only significant shifts in how organizations operate, but also in retraining personnel who are accustomed to conventional computing frameworks. Lastly, there is the matter of regulatory and ethical considerations. As quantum technology advances, it could disrupt existing industries and raise new security concerns, notably in cryptography. Ensuring that quantum applications are used responsibly and effectively calls for developing new standards and policies that can keep pace with rapid advancements. Addressing these barriers will take collaborative efforts from scientists, engineers, businesses, and governments. Through persistent research, innovative ideas, and strategic partnerships, the vision of a future shaped by quantum technology can gradually become a reality. Quantum sensors hold remarkable potential for early disease detection, even before symptoms manifest. At their core, these sensors leverage the principles of quantum mechanics, which allow them to measure incredibly small changes in physical quantities. For example, they can detect minute variations in magnetic fields or temperature changes that might indicate the presence of a disease. Imagine a situation where a sensor can pick up on microscopic changes in the body that occur well before traditional medical tests would ever highlight any issues. This could mean identifying early signs of conditions such as cancer or infections simply through sensing alterations at the cellular or molecular level. The ability to analyze these subtle differences could enable healthcare providers to intervene much earlier, greatly improving the odds of successful treatment. What makes quantum sensors particularly exciting is their sensitivity and precision. They can measure signals that are so faint they would elude conventional sensors. For instance, if the body begins to produce specific biomarkers in response to a developing illness, a quantum sensor could potentially detect these indicators long before they provoke noticeable symptoms. As research continues, scientists are exploring how to integrate these advanced technologies into practical health monitoring systems. With further development, quantum sensors could revolutionize the way we approach diagnostics, allowing for proactive health management and ultimately leading to improved patient outcomes. The future of healthcare may not only rely on treating diseases, but also on predicting and preventing them through the power of quantum sensing technology. Quantum computers hold the potential to revolutionize the way we understand and create materials. Unlike traditional computers, which process information in a binary system of ones and zeros, quantum computers use the principles of quantum mechanics to manipulate data in ways that are more complex and powerful. Imagine being able to explore a vast landscape of possibilities simultaneously, rather than taking one path at a time. That's what quantum computation allows. When it comes to designing new materials, the key benefit lies in their ability to simulate molecular and atomic interactions with an unprecedented level of detail. Traditional computers struggle with these types of calculations because the behavior of particles at such a tiny scale involves an immense amount of variables and complex relationships. Quantum computers, on the other hand, can handle this complexity more efficiently. They can explore numerous configurations of atoms and molecules quickly, identifying promising candidates for new materials that could possess extraordinary properties, like increased strength, lighter weight, or improved conductivity. Furthermore, quantum computing can significantly enhance our understanding of existing materials. It can help researchers uncover new behaviors and properties that were previously hidden, leading to innovations in energy storage, superconductors, and even pharmaceuticals. By predicting how changes at the quantum level can impact the overall characteristics of a material, scientists can tailor substances for specific applications, paving the way for breakthroughs in technology and sustainability. While we are still in the early stages of harnessing this technology, quantum computers promise a future where the creation of new materials with remarkable attributes is not just a dream, but a tangible reality. This could lead to advancements that fundamentally change industries and improve our quality of life. Quantum physics explores the behavior of very small particles, like atoms and subatomic components, while gravity dictates how large objects like planets and stars influence one another. The connection between these two essential fields remains one of the biggest puzzles in modern science. At its core, gravity is described by a theory called general relativity. This theory explains gravity as the bending of space and time caused by mass. Imagine placing a heavy ball on a trampoline. The weight causes the fabric to dip, demonstrating how larger objects influence their surroundings. However, general relativity doesn't incorporate the strange behaviors of particles at quantum scales, such as uncertainty and entanglement, which are central to quantum mechanics. The challenge arises when trying to merge these two frameworks. Scientists believe that at the smallest scales, gravity might not act the same way we experience it on a larger scale. For example, on a subatomic level, the traditional understanding of a smooth space being warped may not apply. Instead, the fabric of space and time could become irregular and fluctuating, influenced by the probabilistic nature of quantum mechanics. Researchers are exploring several theories to bridge this gap. One of these is called string theory, which suggests that fundamental particles are not simple dots but rather tiny vibrating strings, and it incorporates gravity at quantum scales. Other approaches involve concepts like loop quantum gravity, which seeks to describe gravity using quantized loops of space. While no single theory has been universally accepted, the goal is to find a unified framework that can describe all forces of nature, gravity included, within the quantum realm. This ongoing quest for knowledge reflects humanity's desire to understand the very fabric of the universe, melding two seemingly disparate realms into a cohesive understanding of reality. Quantum physics is an ever-evolving field, rich with mysteries and potential breakthroughs. One of the most thrilling frontiers is the exploration of quantum entanglement. This phenomenon occurs when pairs of particles become interconnected in such a way that the state of one immediately influences the state of the other, no matter how far apart they are. Understanding this connection could lead to revolutionary advancements in technology, including the creation of secure communication systems and the development of powerful quantum computers that operate far beyond the capabilities of our current machines. Another captivating area involves the quest to comprehend dark matter and dark energy, which constitute a significant portion of the universe yet remain largely elusive. These enigmatic components do not interact with light, making them nearly impossible to detect. However, quantum theory could provide essential insights into their properties and behaviors, potentially changing our understanding of the universe and our place within it. The concept of quantum gravity, another exciting frontier, seeks to reconcile the theories of quantum mechanics and general relativity, which describe the very small and the very large, respectively. Currently, these two frameworks do not align perfectly, and finding a unified theory could revolutionize our grasp of the fundamentals of space, time, and the fabric of reality itself. Lastly, the study of quantum biology investigates whether quantum processes play a role in biological functions, such as photosynthesis, or the way birds navigate using the Earth's magnetic field. If proven, this could bridge two seemingly distant fields and reshape our understanding of both. Each of these frontiers holds the promise of not only answering fundamental questions, but also unlocking technologies that could transform our world. Quantum advancements hold the potential to transform civilization in ways that may seem like science fiction today. At the heart of these advancements is the understanding of quantum mechanics, which studies the behavior of tiny particles at the atomic and subatomic levels. Unlike the predictable world we experience daily, the quantum realm is full of uncertainty and interconnectedness, suggesting that particles can exist in multiple states at once and be entangled or linked across vast distances. One major application of quantum technology is in computing. Quantum computers can process information at speeds that far surpass our current computers. Instead of using bits, which can represent either a 0 or 1, quantum computers utilize quantum bits or qubits. These qubits can exist in multiple states at the same time, allowing them to perform complex calculations much more efficiently. This capability could revolutionize fields like cryptography, optimization, and even artificial intelligence, enabling breakthroughs that could change how we solve complex problems and handle vast amounts of data. Another area where quantum advancements could reshape society is in communication. Quantum communication promises secure transmission of information, taking advantage of the principles of quantum entanglement. Any attempt to eavesdrop on a quantum communication would disrupt the transmission, alerting the parties involved. Such security could benefit everything from personal communications to global financial systems, ensuring privacy and integrity in a way that current encryption methods do not. Moreover, advancements in quantum sensing could lead to highly sensitive instruments for measuring time, gravity, and electromagnetic fields. This could enhance everything from navigation systems to medical imaging, potentially improving healthcare and our understanding of the universe. Imagine a world where diseases are detected even earlier due to advanced imaging techniques that offer unprecedented clarity. These advancements collectively suggest a future where technology becomes deeply integrated into daily life, drastically reshaping industries such as healthcare, security, and data processing. With each stride, humanity would not only push the boundaries of what is technically possible, but also redefine the very fabric of society as new ethical, socio-cultural, and economic challenges arise alongside these advancements. The journey through the quantum realm is just beginning, and its implications could be as profound as anything we have encountered in human history.